space. And generally, if you look at the solution this way, it means that you are in motion planning. Or you can consider that the solution is an optimal policy. So it's a function from the state space X to the control space U. And if you are searching the solution this way, generally it means that you are in reinforcement learning. And clearly, mathematically, if you have one solution, so an optimal trajectory, for example, you can get the other one, for example, the policy, and reciprocally. So I would like to take advantage of this observation that the two communities are working with two different objects that are the solution to the same problem, to try to see if we can go a little bit beyond what current algorithms are able to. And mostly I would like to give a parcours on the three main bullet points. First, really explore what is the formulation of the problem that we want to solve, what are the properties at which level we want to sit. Then I would like to give a look at the solvers. What are the properties that we can expect from the solvers trying to solve this optimal problem? And I would like also to discuss the connection with hardware, because that's what is really key in robotics. So let's start with the formulation. So maybe give first a quick look at how current state-of-the-art control approaches are set up. A robot control architecture, currently, it's a multi-layer architecture with very different frequencies, starting from the power loop that is running directly on the motor at a very high frequency, like 50 kilohertz. Then a loop controlling either the joint position, velocity, state, or the joint torques, running on each motor boards at quite high frequency as well, and that's joint per joint. Then the first user level, where still at high frequency on good robots, you would decide what is the reference state of the robot or the reference torque of the robot to be applied by the motor boards. Classical formulation here are inverse kinematics or inverse dynamics. And then typically a task space, a task level, where at a lower frequency and using XRO sensor, you can close the loop and achieve more advanced behaviors. So when you are considering this architecture, you can put a learning solution at any level you want. So typically you would put that at the task level. So that's, for example, what we did, but there is many examples in the literature. We are not at all the first to do that. You can do that by to learn where the robot should navigate, so that the lower level part of the architecture would be easy to produce locomotion. Okay, so that's typically what you would expect from the task level, having an abstract behavior that the lower level would be able to accomplish. But I would consider here, I would like to convince you that it is worthwhile to look at the global architecture. First, because mathematically, that's what we want to do. Even if you define a policy at the task space level, what you finally obtain implicitly is a policy at the lowest level. Also, because if you want to optimize any policy, you need to simulate all these behaviors, so you need to understand that properly. And finally, if you want to get any guarantee, the maximum guarantee that you can get on the upper level is the one that is offered by the lower level. So if you want to have a safe control, if we want to have a safe control on the robot, I think we really need to work at the global level. So let's go for the global level. And even if you are not convinced that our algorithms should solve the problem at the global level, you have to be convinced that you have to simulate the behavior at the global level. So to simulate and to formulate the optimal control problem, we need first to describe what is the law of physics on the robot. And the law of physics are well understood. The robot moves with its acceleration, so the derivative of its velocity times its mass, plus some centrifugal and gravity terms, equal to the torque supplied by the motors and the forces applied by the environment in reaction to the torque of the motor. That would be a linear equation, where the main component is the mass matrix here, which has quite a sparse structure. All the white here is zeros, but it's not so sparse. So if you treat that as a sparse matrix, you won't be efficient. More than sparse, it is structure. There is a very strong structure in this matrix. Now, if your robot is, for example, in contact with the environment, you would have also a part of the law that is describing how the contact behaves. And that would add some rows and columns to the matrix and still present a lot of structure. So in robotics, we are very advanced in terms of understanding these structures and providing algorithms or algebra that is very efficiently handling this structure. So not saying that the parameters that we identified or the exact law of physics that we are putting, they are always matching the reality, but the algebra that we have is super efficient. So for example, to handle all the dynamics of the robot, you only need 5 microseconds of computation. Microsecond is really a unit that we are not using very often. So I tried to do a matching comparison, and that would correspond to a network with 4 hidden layers of size 64. So that's quite a reasonable network, a very small one, not a network that would be sufficient to just handle these dynamics. So we put that in a package that is arguably the best software package that is open source for describing the mechanics of robots, called Pinocchio, with the brilliant supervision of leadership of Justin Carpentier from Willow Paris. And I think we are at the point where this software could be a standard for community. So now we have the mechanics described, we can go to the optimal control problem. So again, the optimal control problem would be to optimize X and U trajectories. That is minimizing a cost function, for example, given a bunch of constraints, and here the constraints are playing a very important role. And there is a lot of different constraints. So for example, constraint to impose state feedback, constraint to impose that the obtained trajectory or the obtained behavior match the simulation, and additional constraints of very different kinds, like we could have box constraints, cone constraints, equality constraints, long-term viability constraints. We can even have frequency constraints. So there is a lot of constraints on robots, and we have to render that at the decision level. And too often, these constraints, they are hidden in the simulator, meaning that when you send a behavior that is not matching the constraint, the simulator is clamping your behavior, which corresponds, when you optimize the optimal control problem, it would correspond to a projected descent, which is not a very efficient numerical algorithm. And here, in this optimization problem, we have all the derivatives we want, because all the dynamics have been formulated our way. And with these dynamics, we can have all the derivatives. Since we have all the derivatives, we should expect from our solver superlinear convergence. That's really something we should expect. And if we are not doing the stuff cleanly, then we are not getting this speed. Something that is important to understand is if my want to show my video, is that by modeling the physics this way, we have straightforward generalization. So here you have a robot that is doing a kind of a pick and place task, going from one point to the other. And at simulation time, it has been producing a movement forward. But when it is disturbed, it would discover by straightforward on the flight another behavior backward. Right? And that's just a generalization of physics because we have a strong model. So I think here it's very important that we accept to manipulate this model the clean way. Okay, so that was for the formulation. Let's go now in the solvers. So the first part, and that's the state of the art, let's say, we want to solve to obtain the optimal trajectories. So optimal trajectories are something that you need to replan online at runtime. So for each new state of the robot, you have to solve an optimal control problem. And that's fine because this optimal control problem is not so big. So the state of the art and what is well understood is that the numerical solvers that we are applying to trajectory optimization problems, they should cope with instability due to the dynamics, to the instability of the prediction of an unstable control system. That's the first point. And basically, the keyword for tackling the instability is multiple shooting. And second point, we need to handle the sparsity and the structure because, as you've seen, there is a very strong structure both in the mechanics and in the control problem itself. And we have proposed an algorithm called FDDP, which combines both, so which is optimally sparse and multiple shooting algorithm, and that's in another open source package called Crocodile. And just to give you an idea of the efficiency we can get, if you want to optimize 4 trot cycles of a quadruped, that would correspond to roughly 5,000 variables. You would need 12 iterations to converge to an optimal solution. And for each step of the descent, you would need 4 milliseconds. For a humanoid, 2 steps of a humanoid, you would get 8,000 variables, 18 iterations, and 9 milliseconds per step. Okay, so that's fast enough to be evaluated at runtime, and that's something. So we can have the policy obtained this way, implicitly obtained this way at runtime. Now, the main issue when we are doing the stuff this way is the non-convexity of the optimal control formulation. So for me, it's clear that we won't obtain a convex formulation of the optimal control problem. And then we need to accept that we would get only local solution. And the good way to cope with that is to provide an initial guess, so a good warm start that is close enough to the global solution, so that we can get this super linear convergence to the global optimum. So what we are doing simply that offline we are generating a lot of samples of how the robot should behave depending on initial condition and environment conditions. We are optimizing these samples and we are putting that in a memory of motion, which is just an encoded database. And then at runtime, we are extrapolating a candidate solution from this memory of motion and optimizing from that point. Here is some snapshots of the database that we have generated in the context of locomotion in the European project Memory of Motion, MEMO, that I coordinate. And here is an example on the rail robot. So here we have a runtime optimization of the full body of the robot, tracking a virtual target while avoiding obstacles. And we are using both the capability of the online solver and the memory of motion to provide a new initial guess, especially close to the obstacle. That's very important. That's where the optimal control solver will waste a lot of time to discover a good solution. And so finally, we want to extend this idea by closing the loop and really computing the optimal policy. So for that, what we are doing is that we are sampling a lot of locally optimal solutions. So we are sampling, let's say, 30 states in the state space and trying to connect all these states together. So that would give us something like 1,000 optimal trajectories. But since we are using a locally optimal control solver, we only get maybe 20% of them. The rest of the calls to the solver, they are failures. And on the 20% of solutions that we get, I would say that something like 20% are optimal. So we have only a few numbers of optimal solutions. We are sampling them, so we are taking sub-trajectories to produce a large data set of something like 10,000 locally optimal trajectories that we are just learning by classical regression. Now we can query and get an initial guess of what would be, by extrapolation, possible optimal trajectories to connect two states. And we are just closing the loop. So we are now generating new optimal trajectories from this initial guess. And at every iteration of this loop, we would only be able to get better trajectories. So we are converging down to a minimum, and we are lower bounded by the Hamilton-Jacobi-Bellman solution, which is guaranteeing us a lower bound. So we call this loop iterative roadmap extension and policy approximation, which is a way of computing a policy using optimization and supervised learning. And using this formulation, we can use the derivative at all the stages of this algorithm, and we hope to obtain superlinear convergence that we obtain empirically and that we are trying now to demonstrate theoretically. Let me very quickly finish on applying that to the robot. So there is a first thread of trying to apply that to flagship experimental platforms like the humanoid robot Talos. We just now received the fundings for going to the next generation of Talos, a French grant Equipex. That's very difficult for every single lab to get such a huge platform. That's why I think the way to work here is by working in consortium. And our lab is a hosting experimental platform. So if you need access to such kind of platform, that I think is a solution. An alternative solution is to go with smaller robots like this Open Dynamic Robot Initiative led by Max Planck in collaboration with us and with New York University, where you have a cheap, well, not so cheap, but something like below 10,000 euros. Very efficient. You have a quadruped version, a biped version. Since it's completely open source, it reduces the nonlinear hidden effects, and it's hard to break, easy to fix, so that's very good for machine learning. As a conclusion, three main messages. For me, physics is easy to model. We don't need to learn it. Especially, we don't need to learn the algebra to manipulate physics. So maybe we need to provide strong physics layers in a neural network, the same way you provided strong convolution layers to handle images. So that would be an equivalence for manipulating mechanical systems. When simulating, and any reinforcement learning algorithm now is working simulation, we get the derivative nearly for free. So it would be good to use that to get better convergence properties. And final message, robotic labs are expensive. Let's work in consortium. Thank you very much for your attention, and happy to take questions if there is any, and if we have time.
Thank you, Nicolas. Thank you for this wonderful presentation. Do we have questions? I think we do have time for one short question. I don't see any. I'll ask a question myself. I think your work, Nicolas, actually addresses a very central problem in robotics that has always often bothered me when you see a robot, say, grasp a cup or something like that. I've seen many demos, and you know, it virtually takes forever for the robot to grasp the cup. And when I asked my colleagues in robotics why that took so long, they said that traditional approaches tend to search the entire search space and try to find the optimal policy, the optimal trajectory, and that if you do a complete search over all possible trajectories, obviously that's going to take forever. And I think now what you're promoting is approaches that are significantly faster because they don't do the complete search and they go more efficiently. But I think you highlighted one challenge, and that is that you tend to go into local minima. You also proposed this probabilistic sampling-based approach to get better solutions, and you mentioned that you have 20% optimal solutions in your experiments. But somehow I guess this degree of non-convexity that you have here, or say the number of local minima, that must depend on the type of problem you're solving, right, with the robot. Can you elaborate a little bit what makes the problem non-convex, or what do these local minima correspond to, and in which situations do you encounter more or less local minima?
So non-convexity is very easy to establish. We have an equality constraint which correspond to the simulation. Right? So the simulation is nonlinear, so we have a nonlinear equality constraint. End of the story, it's non-convex. Right? That's very easy. And well, for robot arm, you have a lot of angles. Then you would have cosine and sines. So again, non-convexity. That's easy. Now, what is the level of non-convexity? And that's really difficult to characterize. So basically, we know we are not non-convex, but we are always starting with reasonable solution. Maybe a very simple reasonable solution is a free fall. And even free fall is likely to be in a lot of, in the convergence basin of many optimal control problems. So it's very difficult to characterize. For biped locomotion, for example, we observe a superlinear convergence from the very first iteration, starting from free fall. So it seems that a basic locomotion problem that seems to be a complex problem is still not so non-convex, which is surprising. When we set up our solver, I was not expecting to get that. Now we have a lot of obstacles, or no, not obstacles, constraints. We have a lot of constraints, and that's making the search much more difficult. So yeah, difficult question, difficult to answer, but we have to understand that first, whether you are optimizing the policy or optimizing the trajectories, you get the same issue of non-convexity, and that very likely sampling, so random exploration, this kind of stuff, are going to cope with that, because we would have a lot of solutions answering to problems, and by extrapolating, you would get a very good solution for new problems. So maybe not such a big issue.
Okay, thank you very much. In the interest of time, I'd like to thank you for the great presentation and the question answer. We'll move on to our next speaker, and that is Michael Möller from the University of Siegen. Michael,
Perfect.
the floor is yours.
Thanks a lot. Thanks for the invitation to speak here to you about deep learning and energy minimization methods for inverse problems. So the setting I'm considering is that I would like to recover some desired unknown quantity U from observed data F, whose relation is determined by some kind of problem operator A and some measurement noise N. So maybe in the simplest case, think of just being given a blurry image and a blur kernel to then remove the blur and recover the nice, clean and sharp image. And for several decades, the type of approach to solve these problems have been energy minimization methods, where you determine your solution you had as an argument that minimizes a suitable cost function given by a data fidelity term that measures how well your current solution U explains your measured data F, and a regularizer that tries to measure how realistic U is as an image. Now, over the last 10 years, the research in this field has changed, basically turning away from these approaches and turning towards deep learning, where you just choose some parametric function called a network and try to accomplish the mapping from your data to your desired ground truth in a forward fashion, depending on parameters that you learn through your usual, ideally fully supervised setting. Now, while deep learning is really dominating almost any benchmark in image reconstruction these days, I think a few drawbacks of machine learning or deep learning remain that are not so much present in energy minimization methods. The first one being interpretability. So this is an example of a very low dose MRI reconstruction, where, okay, a classical approach just doesn't give very good results because the problem is so underdetermined. A network-based solution may look really nice at first glance, but looking in detail, there are some problems. Like, for instance, an artificial blob I inserted into the ground truth that was never part of the training data, which is why the network has a strong tendency to entirely neglect it. But even beyond these tricks to fool the network, there are, for instance, some fine, thin structures. And a network-based solution did recover fine structures, but they move into a completely different direction, possibly leaving us with a different pathological interpretation of the images. The second challenge, closely related, is robustness. This is something that is well known for classification networks under the name of adversarial attacks. And it seems that for inverse reconstruction problems, similar effects tend to happen. So this is an example of a very low dose computerized tomography reconstruction, where a standard network on standard data shows really nice reconstruction for the limited amount of data that was provided to it. But changing the input data by only about 3%, we get a very bad reconstruction with even some structures that might be pathologically concerning. The third possible drawback is a limited versatility of such networks. Namely, they don't necessarily generalize well to tasks beyond what they have been trained on. So this is an example of denoising an image with a network that has been trained on removing Gaussian noise. And we see it pretty much perfectly preserves the noise and damps some of the structure of the fur of the giraffe here. So this is kind of a worst possible outcome, and an adaptation that is very easy to make in the world of energy minimization methods, where you know if you're transitioning from something like Gaussian noise to something more impulsive like salt and pepper noise, you just switch your data fidelity term from something like L2 squared to L1 to be more robust. Now, my group has been working on addressing some of these drawbacks by combining energy minimization and deep learning methods, two examples of which I would like to show you now. So, for instance, to address this last issue of versatility, one could consider writing down your favorite algorithm to compute minimizers of, let's say, first a completely model-based energy like this. So, for instance, writing down something called proximal gradient descent would look like this, where you take a gradient descent step on the data fidelity term, this is this inner part here, and then do a proximal step on the regularizer, meaning you're minimizing an L2 squared data fidelity term plus regularizer, and this from a perspective of maximum a posteriori probability estimates corresponds to a problem of removing Gaussian noise and gives rise to the idea of just replacing this step here to become more regular by your favorite denoising algorithm. So for model-based denoising algorithms, this has been proposed under the name of plug-and-play priors, and we specifically considered ways of learning this denoising mapping. And the nice effect here is that we really do gain versatility on the aforementioned problems. So this is again the result plainly applying a Gaussian denoising network on the image gave us. But if we use an algorithmic scheme like this and an L1 data fidelity term, we are in fact able to completely remove the noise here in a realistic fashion with the very same network that has only been trained on removing Gaussian noise. However, this is possibly not yet the end of the story and solves all problems. So for instance, in a follow-up work, we considered what happened if we have a zero data fidelity term and we just keep denoising the image. Are common networks stable? And unfortunately, the answer is not necessarily. So this is what you get after 800 iterations of standard MATLAB's pre-trained DN-CNN. And we can see that instead of converging to something smooth, which you would expect when you just continue denoising over and over again, it actually diverges to very large values and weird structures. To gain more control over networks, specifically in iterative settings like this, we considered controlling neural networks by forcing them to actually monotonically decrease a model-based energy. So this is mostly addressing robustness. So if you have some model-based energy E, we consider training a network that takes a current estimate UK, the data F, the gradient at our current point, and depends, of course, still on learnable parameters theta, in such a way that it tries to predict an update to the current estimate UK. And we do so in a very specific way, namely by ensuring the network proposes a descent direction with respect to the model-based energy. So we would ensure that the network's output actually has an inner product with a negative gradient of the energy, which is, well, think of the right-hand side as zero, so which would be pointing in a similar direction, and to then theoretically guarantee convergence, we need a little more than zero here on the right-hand side. So with this technique and a suitable step size rule, a gradient descent-like iteration, but with a learned update direction coming from the network, actually provably converges to minimizers of the original model-based energy E. Now you may wonder, why would I set up a complicated scheme to then converge to minimizers of a purely model-based energy? Couldn't I just do gradient descent? And I would like to give you two answers why this could still be of interest. The first one is, if minimizers of E are not unique, you might select your minimizer in a data-driven fashion. So this is a toy example where we are just looking for two variables that sum up to 5. And running gradient descent from any starting point will just take you to your solution space in an orthogonal way, indicated here by the flow field. Whereas given training data that might favor one component being 0 and the other one being 5, or being equal to the value that you want to achieve here, you can learn a flow field that actually from any starting point converges to something that lies right in the middle of your training examples. Even if the minimizer of your energy E is unique, it might be of interest to generate a better path, for instance, using something that is called discrepancy principle in inverse problems or early stopping in the context of networks, where you don't fully converge to a minimizer, but stop early depending on the noise you're expecting. And then, of course, taking a trajectory that takes you closer to the ground truth, although it ultimately converges to the minimizer, and stopping early may still give you much better results. Now, these ideas address some of the issues I mentioned in the beginning, but maybe not yet all of them at once. So a natural question for going forward would be, can we resolve all the three drawbacks of interpretability, robustness, and versatility at once? And having told you that energy minimization methods don't really suffer from these drawbacks, a natural question is, can we learn the energy to minimize, and would that resolve all our problems? So learning the energy to minimize would then be something like this, where you have an energy E that is still parameterized by some parameters theta, and you compute the argument that minimizes this energy that I'm calling UI of theta here. And then for training, you are comparing the argument that minimizes the energy with your desired ground truth on your training examples and find the best parameters here. Now, this is a technique which in applied mathematics is known under the name of bi-level optimization. And you may wonder now, does this already solve all our problems? But unfortunately here, the answer is clearly no, because really learning an energy like this without saying something about E has absolutely no advantage over plain supervised deep learning, because it is in fact equivalent to deep learning. By picking the energy, your parameterized energy here, as something like just the norm of U minus some parametric function applied to your data F, you can easily see that the argument that minimizes this energy here is just G of F and theta, which you then plug in here for UI and theta, and you are back at plain supervised deep learning. So it must be the mathematical structure of the energy that makes a difference here. Now, what would be a good structure? Well, having told you that typical model-based energies are comprised of a data fidelity term and a regularizer, with our desire to be versatile with respect to the data fidelity term, it is natural to try to learn the regularizer only. So inserting now maybe into the bi-level formulation I just showed you, just the idea of computing the argument that minimizes the regularizer, and then comparing this argument that minimizes the regularizer to many different training examples. Well, first of all, this is not supervised deep learning anymore, because your regularizer never sees data. But then you may also wonder, how can I compare the argmin here to multiple training examples? And the answer is, of course, now your regularizer should be, sorry, the set of minimizers should be really set valued. So many different U's should be minimizers of R here. So this loss here compares now the distance of a set of minimizers U of theta to specific elements UI star. Now, if you want to pursue this kind of direction with this kind of structure, I think we are very close to the challenges that we heard about in yesterday afternoon's talk by Yann LeCun, at least in terms of the first two challenges that I will point out now. Namely, the first challenge would be to avoid the collapse to the set of minimizers being everything. Because of course, if your regularizer here is entirely flat, then the argument that minimize a flat regularizer could be the entire space. and then I'm comparing the distance of the entire space to specific elements. This would give me a zero loss here, so it would be a perfect solution. So we need some kind of technique to tell the regularizer to go up once we move away from training examples. However, we also want our regularizer to not go up too fast, because otherwise we run into a different collapse, namely one where this arcmin set are the training examples only, or from a probability point of view, we are converging to just the sum of delta peaks at the training examples. So this does not generalize well and is overfitted to the training data. So we want it to increase, but not increase too fast, are the first two challenges. The third challenge is basically to do the numerics or optimization or mathematics. So we need to compute an arcmin through a second arcmin operation. And the fourth challenge that I would like to end with is what a good structure of the regularizer itself is, because of course we are not in the setting of plain learning anymore, but for mathematical analysis like robustness, we would ideally like our regularizer to be convex. But from a practical perspective, convexity doesn't make any sense, because it would tell me if I'm averaging two realistic images, I get something that is at least as realistic as one of the images I started with, which is clearly not the case from a practical perspective. With this, I'm at the end of my talk. I would like to thank you for your attention, and I'm happy to take questions or propose solutions to the challenges I raised. Thanks.
Thank you, Michael, for this nice presentation. We have a question from Jean-Bernard, I think.
Yes, thank you for a very nice talk. And it reminds me the latest issue of SciAm News on machine learning. It was March, I think, or April, where there was this, especially in machine learning techniques for inverse problem, exactly as you are pointing out. And they were mentioning this instability theorem, saying that if you learn very well, then you are unstable. There is a compromise, a trade-off, which is unavoidable. And it was very nicely explained with this Lipschitz constant of the input-output map of the network. Can you comment on that, or?
Yes, I think this is a promising direction to enforce some kind of Lipschitz continuity. Now, from the perspective of energy minimization methods, we would expect a different metric. So typically the way Lipschitz continuity is enforced in networks is by in an L2 sense. So L2 perturbations of the input should cause small L2 perturbations of the output, whereas the corresponding robustness error estimates in energy minimization methods would take a very problem-specific metric for this Lipschitz continuity that is based on Bregman distances of the regularizer, in fact. So I see a challenge of adapting our understanding of Lipschitz continuity for neural networks there.
Okay, we have a second question from Christian.
Yeah, Michael, thanks for the talk. So I just wanted to understand or point out, I don't know, I mean, there is some work in the maybe more AI literature on what is called constructive machine learning, where they also think a lot about parameterized loss functions or energy functions or whatever. And one part they were quite interested in is in getting a bit of a solution to maybe also what was the question just a second ago, by asking the human, the designer, once in a while. And could that, I mean, don't get me wrong, I'm not now saying we just ask always humans and that's the solution to everything. But I think it's quite interesting to once in a while get a bit feedback on how should I change the loss function. And we don't do it in mathematical terms, but by asking questions about the examples. And so I was wondering whether there has been already some more work in that direction in the computer vision community. So that is one part. And the other part is, I like the idea to say, let's learn the regularizer. There's some other work on what is called probabilistic circuits, where people now make use of a tractable probabilistic model that can accommodate for logical constraints. And I think that might be also very interesting to ask, how can we put general, sure, it's logic, I'm sorry for that, but constraints onto our problem, like whenever this happens, don't do that. Whenever that has happened, don't do that. And you can put even a bit of reasoning in there. So, but the first part is maybe more interesting. I'm not sure. I'm wondering about that.
Yes, so thanks a lot for these comments. Absolutely. Specifically, what? Okay, sorry, my connection just broke. Specifically, I think the issue of interpretability is hard to solve without humans, because really in terms of an L2 metric, the example I showed from MRI reconstruction, the network gets good scores. So it really depends on maybe even a medical expert to tell us what to look for and maybe provide some feedback in this sense to really get improve there and make it measurable or have some other type of feedback. I'm not so much familiar with works in this direction in the computer vision inverse problem community, to be honest.
So what we were doing, but we can take it offline. We were looking at visual explanations, and then you can check it. I got reminded when you were showing, okay, here there's some part in the image that is reconstructed, but in the wrong way. And then you may just say, look, this reconstruction looks good, but it doesn't make sense, and you may have to shift it somewhere. And you put this bit of knowledge into your system again. In a sense, you're changing your loss function, and the learner gets again motivation to keep going with learning. But yeah, let's take it offline. It's super interesting.
Okay, yeah, I would love to, because this is perfect. This is exactly what I'm interested in, combining knowledge that we have with machine learning.
Yeah.
Thank you, Michael. Thank you, everyone, for joining the lively discussion. We'll take a break now, about 15 minutes, and we'll reconvene at 10:10 with the talk of Klaus Müller. Thank you.
Hello, everyone. Welcome back after the coffee break, and welcome to the second part of the Tuesday's symposium. So our first speaker is Klaus Robert Müller, talking about machine learning meets quantum chemistry. Please.
Yeah, thank you very much for inviting me, and thank you very much for organizing this wonderful event. So I've enjoyed myself very much listening to talks before. So today I will mainly focus on the sciences. So in Berlin we have a high activity for machine learning in the sciences. That is physics, medicine, and chemistry, which is what I will be putting the focus of this talk on. And I will talk a bit about the history of how this came about. And the bottom line, which is also something that translates to other disciplines, not only chemistry, is that you can include some knowledge, physical knowledge in this context, to obtain higher accuracy and less data. And you know, and there are some disciplines, not computer vision, where you have few data points because they're very expensive. So what I'm talking about is highly interdisciplinary, and I will try also to show that from machine learning models you can extract novel insights, and novel means that you didn't know them before. So first is joint work with these people, Matthias Rupp, Anatol von Lilienfeld, and Alex Tkachenko, and many others, but they were the first movers. And so the story was that I had my sabbatical in 2011 at IPAM, Institute for Pure and Applied Mathematics at UCLA in California. And this is a wonderful place to go. So if you ever get invited to this place, please accept. They have 3-month programs, and usually if you come as a professor somewhere and have your sabbatical, then everybody around you is busy doing the standard things, like teaching and minding their business. But in IPAM programs, there's typically a dozen professors from all over the world bringing some postdocs, and they are, confined to this, terrible place in California with nice weather all the time, and they have nothing else to do than to do great research. So when I arrived there, I realized that everybody around me was either a theoretical physicist or a chemist, and I was the only machine learning dude. And then they talked a lot about quantum mechanics, and I realized that I had a training in quantum mechanics back in the days, which made me young again. So what they were talking about was Schrödinger's equation, and you see it next to the face of Schrödinger. It's a very innocent looking eigenvalue equation, but if you would naively solve it, you would have to solve a 10 to the 60 dimensional eigenvalue problem, which of course you wouldn't. So this is really a beast, this equation. And so what people do is they do some approximations. One is called density functional theory, and that got a Nobel Prize. So basically you try to take whatever is you have, like a molecule or a material, and if you have a molecule, then it consists of atoms, and atoms have some positions and some nuclear charges, Z and R, and that's what you put into the Schrödinger equation, and out you get some quantum mechanical properties like energies. So the idea of these approximations, like density functional theory, is that you do all first principle theoretical physics, and in some point you make an approximation. And so I said, well, how about just not solving the equation, but rather predicting the outcome of the equation, which is of course something that typically you don't do, and people in math and physics, they don't really appreciate this. And so this is what we suggested. And so essentially putting the same which goes into an equation into a machine learning model and predicting. And so just to say why this makes some sense is if you do density functional theory for a small molecule, it takes about 3 to 5 hours of computing time per molecule, per data point. And if you have a material, then it takes about 4 months of computing time. Whereas if this stunt with the machine learning model would work, it takes less than a millisecond for a forward pass. So the way we went about was we coded, so to say, each atom by a nuclear charge and position, and then because you need to describe a molecule in some way, and we described the molecule as a matrix, and then which takes the differences between the positions of the atom, of the ith and the jth atom, and you can recognize the Coulomb force here. And so that gives the Coulomb matrix. This was the starting point that we thought about in this IPAM program. And then, of course, if you have two features, then in this case, two matrices, you take the Frobenius norm, and then you, at that time, we took a kernel ridge regression model. So you put it into a kernel, and then you solve the kernel ridge regression model. So since you have, if you can afford it, few thousand data points, this is a piece of cake. So the interesting thing is that we got quite nice results. So we arrived at out of sample predictions of quantum chemical properties about quality of 10 kcal per mole at that time. And this was surprising, but more surprising is that we are now with more sophisticated methods below 1 kcal per mole and precisely 0.2 kcal per mole. So out of sample. And so this means that within fractions of a millisecond, we can explore and predict across chemical compound space. So we gained a factor of something like 50 million overall by now, and maintain the precision. So if we dream a bit, and we saw the nice nebula of Yann yesterday in the background. So people have been charting, having been making maps of the stars throughout our times, but there is no map of chemical space. Chemical space is vast. Even if you take only small molecules, there's more small molecules than atoms in this universe. So because to know their properties is completely unfeasible with standard quantum chemical procedures, but with machine learning, we couldn't start navigating this chemical compound space. So this is a huge thing, and machine learning plays a key role in this. So just to give you a bit of a background about more interesting architectures and kernel ridge regression, that was the first part. It was a tensor neural network by Christoph Schütt and collaborators. And here, basically, the idea is a bit like in embeddings, like word embeddings, we say in natural language processing, word to vec. So the idea would be to say, instead of learning to embed a word in its textual context, we try to learn how to embed certain atomistic properties in its chemical context. So across the graph of bounds that the molecule has. So basically, also again, we have the distances between the atoms. We have their nuclear charges. Then we start embedding, and then we start adding interactions, and then we have a layered architecture, which in the first step describes the atoms, in the second step the bonds, in the third step higher order interactions, and so on and so forth. And with that, we learn from the data how to embed this information, and voila, there's the deep tensor neural network that has something like 0.3 kcal per mole prediction quality. Now, the interesting thing, and since I'm not talking about this much, is that there's now a set of techniques that allow to explain what neural networks actually do. And if you do some neural networks in the sciences, you should be better know that it's doing the right thing. It's not, you know, feeding of artifacts. And so it's highly important if you work in the sciences to really know that everything is okay. And so here we analyze the tensor neural network and make these gummy bear plots that you can see, the colorful ones. And so in a way, we compute something that is, and I put this in quotes, a chemical potential. So imagine you put yourself next to the benzene, like here, and you would be a hydrogen. Then what our model gives us is, you know, what kind of chemical potential in the light of what the model has learned is experienced. And so this is something that the model was never trained for, but for a chemist, this makes a lot of sense. And of course, you can also do the same thing for materials, and you can see this down there. Now, having a new neural network architecture on one side, that's nice, but you know, you make chemists happy. The question is, you know, is this a one-way street where you use machine learning for chemistry and that's it? Or is something coming back also to machine learning? And so one of the things, this is another architecture, it's called the SCHNET. It's a convolutive neural network. And typically in computer vision, you always have discrete filters. And if you think about a molecule, how it's wiggling, then you can easily think about a situation where the atom position have changed just slightly, but the filter gives the same answer. And so we came up with the concept of continuous filters, and that actually made a huge difference in that context. But you know, going back, a number of people, once this architecture was established, have understood that, you know, they can perhaps use this. Okay, so this is really a novel ML model, and it was also appreciated in the machine learning community. So if you would, you know, do computations, then, you know, on a silly laptop, you know, you can do you know, very long trajectories of molecular dynamics, you know, in 7 hours, which you can do before only in 7 years of computing time on a supercomputer. So this is a huge difference at, of course, you know, the same quality. This is the architecture. And so because I have been already using molecular dynamics as a concept, so what is this? And what is the machine learning problem there? So now we are not navigating chemical compound space, but we are actually analyzing a single molecule. So the single molecule, as I said, does dance, changes its configuration. And with every change in the configuration, it has different energy. So you can think of this 3n, n being the number of atoms, dimensional space, with energy values attached to it. And so what the idea is that you would like to sample this space to understand, you know, where the minima are, and you know, what the potential energy surface is, because if you take the gradient of this potential energy surface, you know where the molecule moves. And if you follow this gradient, then you have something which is called molecular dynamics, because you can see the molecule dance. But for this, you need the surface. So for a standard molecule like aspirin, you would need about 50,000 samples in order to get a decent surface. So if you think about this, it's quite a lot of computing time. And if you then use this data, then you could actually do a regression model that makes you approximate this surface. And once you have the surface, then molecular dynamics is a piece of cake, because you just follow the gradient. So one of the interesting things here is if you again do take aspirin as an example, then typically you have about 50,000 samples that you have to sample from your potential energy surface in order to do a decent regression. But if you remind yourself that in this universe, the law of energy conservation holds, this differential equation that you see in the middle of the slide, then you can show that the architecture can be changed slightly, but fundamentally, and you don't need 50,000, but only 1,000 data points. And if you take into account the rigid and non-rigid symmetries of the molecule involved, then you only need 100 data points. Now, 100 data points of 5 hours, this is a piece of cake. But these 5 hours correspond to a lightweight approximation of the Schrödinger equation. If you take what is called coupled clustering, coupled cluster solution, then it's called CCSDT. Then it takes between 1 and 7 days for such a molecule. So 50,000 times 7 days, no way. But 100 times 7 days, that's okay. And so practically, we have been training these force fields at the high accuracy of CCSDT. And that actually starts to coincide with the experiment. The lower, cheaper approximation don't. So this opens a huge new field. But the interesting point here is that you include physics and symmetries and invariances to get there. And so let me just go to show you one video, which is some very other type of machine learning, which is a collaboration that we did with our colleagues in Jülich. So probably you have heard about these scanning probe microscopes, and you can basically use them. You have some tip with which you can lift atoms from a surface, and then you can write funny things like Jülich on the surface. This is real, right? So you lift up an atom, and then the atom is gone from that part of the surface, and then you can you do these funny writings. So the thing is that our colleagues Christian Wagen and Stefan Tautz, they're very interested in building stuff with atoms or with nanoparticles. So you can lift up a single atom and build things, but this takes a long time. So if you would be able to lift up a larger molecule, like on the right, then it would be much easier, because you could just do nano Lego if you want, right? And so what we're doing is we have some molecules on the surface, and then there's this one atom tip that tries to lift these molecules. The problem here is that the lifting is difficult. So a human who is very well trained can do this 2 or 3 times out of 50. Right, so this is not very practical if you want to play nano Lego. So what we did was we trained a reinforcement learning, again with very few data points, because there's not much experiments that people can do. Every experiment takes about 5 minutes or 10 minutes, so that's not going to give you many data points. And then we can actually have the reinforcement learning learn how to actually extract the molecules from the surface, and you can see a video from that. And in the beginning, this doesn't work. The tip breaks off. And by the way, the tip changes at every time when it breaks off. And so, so you can see that the movement is actually, not so trivial. And you with an appropriately trained reinforcement learning algorithm, we are getting to this nice extraction. And we're now at something like 48 out of 50 where we are successful. So that's basically a proof of principle that we can indeed play nano Lego. So I've told you a bit about the quantum chemistry. The physical priors, they are very, very useful, and they can be also, the concept can be also used in other contexts. It makes chemists superbly happy to be able to have very accurate force fields. And of course, one important point is that we have to understand what our model does, and we have to make sure that it doesn't do any nonsense or clever Hans stuff. And there's novel machine learning models that were motivated by physics, but came back to the neural network community and make people happy there. So thank you very much. If you want to read a book on the snapshot of what we have been doing, that's this one, or the explainable AI one is this one. So please, if you have questions.
Perfect. Thanks a lot for the very nice and interesting talk. We have questions, but I'm afraid we have to postpone them to the coffee break to roughly stay in time. So I'm really sorry, Jean-Bernard Lasserre, but maybe we can postpone this to the break and move on with your talk.
I'm happy to answer any questions, so just chat to me on.
Perfect. That is also a good option.
Okay. Is that,
yes, so that is perfectly visible.
yes.
Yes. So Jean-Bernard Lasserre will talk about the Christoffel Darboux kernel for data analysis. Maybe I'm mispronouncing this. Please, stage is yours.
Okay, thank you very much for the invitation, and I'm glad to talk about this topic, which is relatively new for me also. I've been working on that for, let's say, 3-4 years only, and it's a nice also realization of the French-German cooperation, because these two guys on the left, you see Christoffel, he was in Berlin. I think it was he started this school at the University of Berlin a long time ago, and then even Technical University of Berlin later on. And Darboux is a French guy also, so it's this guy from the 19th century. And the talk is about exactly, you see this kind of points that make the C of Christoffel, the D of Darboux, and the red line is what is called the Christoffel-Darboux polynomial. I will try to explain how this tool, which is quite simple to use, could be useful in some application in data analysis. So this is a joint work that has been done with two collaborators, one from France, Edouard Pauwels from Toulouse, and Mihai Putina, who is in UCSB in Santa Barbara. And this all my talk is based on material that you can find in this forthcoming book, should appear in the middle of this year. So just to introduce the topic, just consider a cloud of two-dimensional points, like the points in the figure above. And you see this red curve. It will be the level set of some polynomial, which is quite simple to construct, and you see that it captures very well the shape of the cloud. Okay, and in fact, surprisingly, this even with low degree D, because this polynomial is parametered by its degree, you can play with the degree of this polynomial. And the nice thing is that even with a low degree, you can capture the shape of many different clouds. You see a bunch of cloud of points, two-dimensional points, and you see for each example, I don't know if you carefully see in the slides here, but you see the red level curve is a certain level set of this polynomial, and you see that it captures very different shapes, so it's not a coincidence. So if you want to play with it, you can do it in a very simple manner. So you generate any cloud of points. Of course, it has to make some geometric shape to see some striking result. So you draw your favorite cloud of points. Okay. Once you have your data points in 2D. You just construct this polynomial. You fix the degree D of your polynomial, and then you look at the basis of monomials in two variables up to degree D. Okay, one, the linear terms, quadratic terms, and degree D terms. Okay. So then you construct the empirical moment matrix associated to the cloud of points. So you take each point, xi. You take the VD of xi, VD of xi transpose, and you make the sum. So it's an empirical moment matrix. So you sum up over all points of your data set. So typically here, the empirical moment matrix associated with the measure mu(n). Okay. Usually the point could be drawn from some measure here, but just you don't even need this assumption. And now you form this polynomial of degree fixed D. So you invert the empirical moment matrix, you take the inverse, and then you, on the left and on the right, you multiply by this vector of monomials. So in doing so, you obtain a sum of square polynomial, and then you plot some level sets. You look at the set of x in R2, so that Q of D of x is equal to gamma. And in particular, there is a very standard level set to look at, which is this one. And this level set is exactly what you see here. Okay, let me go here. It's exactly this level set. So it captures the shape of your cloud points. So in fact, the Christoffel function is a reciprocal of this polynomial. So it's 1 over this polynomial evaluated at x. Okay. And in fact, this is an old tool which is quite known as a rich history in approximation theory and theory of orthogonal polynomials. And main contributors in this domain are by Nevai, Totik, Kroh, Lubinsky, Simon. But apparently, this Christoffel function is not so well known in data analysis. And it's because maybe this tool was in approximation theory and orthogonal polynomials is usually not associated with cloud of points, discrete measures. You start from the beginning from a measure, and then you analyze some Christoffel-Darboux kernel, but you don't start from a set of data points which is discrete. So maybe that might be a reason why people in the two communities were ignoring each other. So let's start about a little bit of mathematical setting. So given a measure mu on a compact set omega in RP, so you are given a set omega in RP and a measure mu on this set, okay, supported on this set. And then the vector space of polynomial up to degree D can be viewed as a subspace of L2 mu. And it's a reproducing kernel Hilbert space, okay? And this reproducing kernel is just this one, a classical one. You take all the orthonormal polynomial P alpha up to degree D, and then you take this P alpha of X, P alpha of Y, and you sum up about all orthogonal polynomial of degree at most D. This gives you a kernel, and this is what is called the Christoffel-Darboux kernel. So it's very classical, okay? And it's a reproduction kernel Hilbert space. So what are the nice properties of this Christoffel function or this Christoffel-Darboux kernel? So one way to see the Christoffel function is just that the inverse of this Christoffel function is just the diagonal of the kernel. Okay. And it has also some variational formula. So if you take the point xi, no matter where it doesn't need to be on support, it could define everywhere in RP, right? It's just you look the value of this Christoffel function at the point xi. It's just looking at the polynomial of degree d that minimize p squared d mu, given that its value is 1 at the point xi. So it's another definition of the Christoffel function. But importantly, and for our applications, what is nice about this Christoffel function, and that's the main message to be remembered, is that it identifies the support of the measure. This is the main point. And you see it's summarized in this theorem that says that if you look at a point inside the support, okay, and it behaves like the value of the Christoffel-Darboux kernel or the Christoffel function at this point inside the support behaves like d to the power p. Okay, p is the dimension of the space, and d is the degree of your order. And what is more important and crucial is that outside the support, when the point x is outside the support of the measure, then it has an exponential increase. It's growing like an exponential. So in other words, if you increase the degree of your polynomial, then the Christoffel function, which is the inverse of this polynomial, goes to 0 very fast, which is not the case for when you are in the support. So this Christoffel function is a way to discriminate the point in the support and the point outside the support. Giving the score of your Christoffel function, you can detect whether you are in the support or outside the support. Typically, what you have in dimension 2, just to summarize, if you are inside the support, the Christoffel function behaves like d to the power p. Some strange behavior, I mean, particular behavior on the boundary, but still polynomial. Okay, and which is really important is that outside the support is an exponential growth. Okay. Other results about the Christoffel function is that, for example, if you have two measures, mu and nu, with the same support omega, and these different densities f mu and f nu, what is nice is that under some weak assumption on the two densities, the ratio of the two Christoffel function converge to the ratios of the densities. Okay, and if you accept more restrictive assumption, and this is a pointwise convergence, and if you have even more restrictive assumption on omega, then you can even show that for one particular you don't need a ratio, but for each point xi in the support, then the Christoffel function is converging to the density of the measure mu times some density, which is proper to the set omega. It's intrinsically associated with the set omega, and it is called the equilibrium measure. And this kind of results can be useful for density approximation. Another thing which is nice is that if omega is not fully dimensional and is supported on a real variety, for example, then if your degree is sufficiently large, not too large, depending on the degree of your variety, then if you look at the kernel of this moment matrix, empirical moment matrix I was mentioning, then the rank of this matrix behaves like a polynomial, which is called the Hilbert polynomial associated with the variety. And so the degree of this polynomial gives you the dimension of the variety. So this is quite useful for manifold learning. Just by looking at your data and the rank of your matrix, you can have an idea when you see the evolution of this rank, and it gives you the dimension of the variety on which your points are. So this is why this Christoffel function could be useful for some application in machine learning. For example, for outlier detection, density approximation, manifold learning. And in this case, since we are in data analysis, the measure mu is an empirical probability measure mu, and because it is associated with a cloud of finitely many points. And this is maybe why people have not, in data analysis, have not looked at this tool, because this tool is usually associated with a classical measure on a compact set. Now, what is nice when you have a set of data points, computing the Christoffel function requires only one pass over the data, and there is no optimization. I like optimization, but in this case, we don't need optimization. And for instance, if you want to use the Christoffel function to detect outliers, it's just, for example, you take a point X anywhere in the plane, and then you evaluate its score with the Christoffel function. And if the score is below some level, the red level in the picture I was showing at the beginning, then you decide that your psi is an outlier. And then this very simple strategy, even with relatively low degree D, is as efficient as more elaborated techniques and with no optimization involved. We have some traces of these results in this paper here. Okay. Well, there are other kernels in machine learning which are not Christoffel Darboux kernel, not even polynomial kernel sometimes, and we can be very efficient for calculating approximation of function in large dimension. The CD kernel cannot do that because it's still, even if the computation is simple, you cannot do to dimension, let's say, more than 20 or 30. However, this kernel in the machine learning community, like the Gaussian kernel, for example, are not related, or at least directly, to an underlying measure supported on the data points you are dealing with. And what is the distinguishing feature of the CD kernel is its deep connection with the underlying measure. That's really the distinguishing feature of the CD kernel. It does not only encode the cloud of data points, but it also captures many essential features of the more complex measures supported on the data points. So if you have a bunch of data points, but behind there is an underlying measure, if your points, of course, are drawn from this distribution, and the Christoffel Darboux kernel, even with low degree, capture many essential features of this measure. So well, in one way, should be seen as another item in the arsenal of kernel method in machine learning. Let me show you, to finish the talk, about the typical approach, how this can be used for approximating discontinuous function, which is hard. It's a hard topic, right? What would be a typical approach? Suppose you have the step function here in red, and a typical approach to approximate a function given by only some sample or some moments would be to approximate the function by projection in some function space. For example, in L2 of mu, L2 of 0, 1, you would approximate this red function by this projection on L2. And of course, this is nice, some nice property of L2 convergence, but it has some bad behavior in the sense that you have typical Gibbs phenomenon. So you have those typical oscillations that appear when you have a discontinuity point. There have been some other positive kernel with better convergence properties that have been proposed, still in the same framework of approximation. But those kernels have some nice property, but they lose the reproducing property. So but they have nice advantages. For example, they preserve positivity when you want to approximate a density. If you want to approximate a density with the oscillation approximation, the result could be negative at some points. So with this modified kernel, like Fejer-Jackson kernel, you can preserve positivity and still have better convergence property than the CD kernel. In particular, you can have uniform convergence for continuous function on arbitrary compact subset. Now, let me show you what you could do also, what you could do with the Christoffel Darboux kernel, an alternative approach. Okay. The way they do it with the L2 norm approach is, in fact, you approximate the Fn by this function f hat of n, which is using the Christoffel Darboux kernel. Okay, and this is produce the oscillations. Now, a counterintuitive detour, instead of considering your function as from 0, 1 to R, your density you want to approximate, okay? The set is, the idea is to consider the graph in R2 of F. So now instead of considering F on the real line, you consider the graph of F on R2. Why are you doing that? And now you consider the measure, which is not on the line, but it's on R2. It's a degenerate measure because it's just the measure which is supported on F, right? So it is a curve in R2. Why should we that? As it implies going to R2 instead of staying in R. It's because now, if you think at this measure, phi, the support of phi is exactly the graph of F. And we know that the Christoffel-Darboux or the Christoffel function is very nice to identify the support of a measure. So if you now apply the Christoffel-Darboux technique to this new measure in R2, which is completely degenerate because it is supported on a curve, then you do what we did before for the cloud of points, right? You define this matrix, okay? This is sum of point xi, fxi. Now you are in 2 on the line for the point, and f of x is on the y-axis, okay? You do that only on one pass on the data. You compute the Christoffel function, and then you approximate f by, at a point x, what is your approximation? Is just the argmin of this function. You look for the y that minimizes this. And then you get very nice pointwise convergence, L1 convergence as the degree D improves, okay? What we cannot do with the L2 approximation. And let me give you just an idea of how it works. For example, the step function here, you see, you don't see any oscillation anymore, even with very few, with a very small degree D, you find the exact matching of the step function. And for example, this one is a very nasty discontinuous function. And then you see, except here maybe, but you nicely approximate your function just by this simple tool of inverting this moment matrix on the sample, on the sample of points of your function. Thank you very much for the attention.
Perfect. Thanks a lot for the very nice talk. We have time for one quick question. Maybe one question from my side. So you showed that the Christoffel-Darboux function is very useful, for instance, for identifying the support of a measure. If I'm now considering this discrete case of samples from such a distribution, how am I still, or in what sense or to what accuracy am I still able to determine the support of that measure? Maybe I missed that part, but.
Yeah, well, no, but well, of course, if there is a nice, in the case your measure is discrete, it's a sample from a measure, then there is a compromise between the degree D and the number of points in your sample. Because if you take a few points in your sample and you take a very, very large degree, what would be the result? The result would be trivial. It would be just very small balls around each point. So, which would not be meaningful, it would give you no indication. So there is a nice compromise, which can be mathematically quantified. How you choose the size of your sample and your degree to still, when D increases and your sample, the number of points in your sample increase, you keep this empirical Christoffel function is still converging to the Christoffel function of the underlying measure. So there is, of course, a compromise to do that if you have this asymptotic analysis.
Okay, perfect. Thanks. Yeah, thanks again. Then let's move on to the final talk of this session. So Matthias Hein.
Okay. Good, can we see it?
Yes, perfect. So Matthias Hein will talk about out of distribution aware training for robust representations, please.
Yeah, thanks a lot for the invitation, and thanks a lot also for organizing this event. So I will present a bit of work on out-of-distribution detection, which we have done in the recent years, where the focus is actually on getting reliable confidences everywhere for a given classifier. And then in the second part of the talk, I will also show how this out-of-distribution awareness actually also improves subsequent tasks like open world semi-supervised learning. Okay, so we clearly have seen in recent years tremendous success of deep learning in various applications like autonomous driving and personalized medicine. But what these applications have really in common, and what makes this also critical, is to some extent that they are safety critical. So we have, errors can have fatal consequences, and that's why we have really high requirements regarding safety, robustness, and security. And despite their success story of neural networks, they also come with a lot of problems. And one of the problems, and that's the main topic of this talk, is that they are overconfident for out-of-distribution inputs. So what does that mean? So you train your classifier, let's say on CIFAR-10. This is so this is noted here by this plane, and then you get an in-distribution image like this dog. And the classifier also predicts this correctly as a dog and is very confident. So what I plot here is the predicted probability associated to this class. This is what I call here confidence. Now the problem is that if you feed now an out-distribution image into the classifier, which is completely unrelated, so it's not part of one of the classes, so this chimpanzee image is not one of the classes of CIFAR-10, then again the classifier produces here a prediction of dog, which is clearly wrong, and it is very confident in this. And this is clearly a problem in safety critical systems because the confidence of the classifier is not reliable for example, triggering human intervention, or let's say in an autonomous car to transfer into a safe state of the system. And clearly, for example, in a medical diagnosis system, you don't want that, let's say you get a new disease, which you have not seen before and which you clearly have not trained on, that then the classifier assigns very high confidence in a given disease. And basically, this unknown disease would, for example, be unnoticed in your system. Yeah, so you really want then that the system triggers that it has no idea what this is, and then basically calls for human intervention. Now, clearly, this problem has been addressed, and one of the state-of-the-art methods is here this outlier exposure, which basically works by during training you have an out-distribution training set, and you enforce basic uniform confidence on this out-distribution training set during training. And then again, you predict well on the in-distribution, also achieve here high confidences. Now you also assign low confidence to this chimpanzee image. So this is a 10-class data set, so 10% would be uniform. So this is very good here. But again, this outlier exposure is not adversarial robust in the sense of now we can just try to maximize the confidence in a neighborhood around this given image. And again, then this produces a very high confidence in the wrong class. Okay, before I basically come to how we address this in our works, I want to briefly explain why we have actually, or why this phenomenon of overconfidence is basically unavoidable. And for this, we basically look now at the class of so-called ReLU networks. These are all networks which just use ReLU activation function. But basically, these are all networks which in the end produce a piecewise affine function for each output unit of the classifier. And such a function is called piecewise affine if there exists a finite set of polytopes such that union of these polytopes is the whole set.
Matthias, sorry to interrupt. Could you lower your volume? There is quite some resonance in the audio.
Okay, yeah.
A little bit.
Sorry for that. I have to stop here screen sharing for a moment, sorry. Is it now better?
Yeah.
Yeah, okay. Good. Okay, so yeah, and so you have this finite set of polytopes where the union is the whole set, and on each of these polytopes, which are then called linear regions, the function is affine. And because, and here one sees basically here's is a restoration of the linear regions of a one hidden layer network in R2. And the problem is that because of you have a finite set of polytopes, these polytopes basically have to extend to infinity, some of them. And on these polytopes, basically the classifier or the deep neural networks behaves then basically like a linear classifier. And this is exactly the problem which leads then to the statement here on this slide, which basically says the following. So you can take any point in RD and any epsilon larger than 0. And then under a very mild condition on the network, on the weights of the network, for any alpha larger than 0 and a class K, you can construct an upscaled vector set, alpha times x, such that for this upscaled vector set, it holds that you can achieve close to confidence 1, arbitrarily close to confidence 1. And asymptotically, as you move basically to infinity, the classifier gets more and more confident. Basically, it gets asymptotically confident for sure. And this is exactly the opposite behavior what you would like to have in practice, because as you move away from the training data, the classifier should get clearly less confident in its prediction. But here's exactly the opposite. So you get more confident, which is clearly completely wrong. And this is not just related to the radio function, activation function, but it can also be generalized to other activation functions which are frequently used in practice. Also, temperature rescaling, which has been proposed for calibrating neural networks, does not solve these problems. Now, clearly one can ask the question, are all classifiers like this? No, the answer, there exist classifiers which then, as you move away from the training data, you get less and less confident. For example, RBF networks are one particular example of this. So, but for really neural networks, you clearly, in order to overcome this phenomenon, you really need to change the architecture to solve this. Okay, but before I come to methods how we did this, first I want to propose this one way to mitigate this problem is basically that we do a kind of an adversarial training on the out distribution. So what does that mean? So here we have our normal in-distribution loss. So let's say just the cross-entropy loss for our training data. And now we have here an additional term which tries to enforce uniform confidence. Now not just on the samples, on the out distribution training samples here set, but even in a neighborhood around this out of distribution training sample. And the nice thing is that in contrast to adversarial training on the in-distribution, basically you do not lose much prediction performance in this way, but you get basically good now performance of or low confidence even in a neighborhood around out distribution points. And that one can see here now with this example. So now ACID would be the new method here. It performs again well on the in-distribution task, but now it produces low confidence on this chimpanzee image, and also in the neighborhood around it, it produces low confidence. The problem of ACID clearly is that we have no provable guarantee. So we can just do empirical evaluation of this, but we have no provable guarantee. And if it really is about safety critical system, clearly the goal should be that we have in the end provable guarantees on our machine learning system. So CCU, which I cannot explain in detail, is another method which we propose, which comes with the asymptotic guarantee to have low confidence far away from the training data. But unfortunately, this still does not imply that on close out distribution training sets, you have this guarantees for these particular points. And so the question is basically, can we guarantee low confidence even in the neighborhood of close out distribution images? And the answer is yes. And for this, basically what we are using is a technique which has been proposed in certified adversarial robustness for the in-distribution, namely interval bound propagation. And the idea is basically that then during training, we minimize an upper bound on the confidence in the neighborhood around any of our out distribution training points. And then again, we use a very rich out of distribution training set. Typically, we always use the 80 million tiny image data set, which is then a proxy of all natural images to have a good covering of all possible images. Okay, so what is this interval bound propagation? It's a very simple technique to get guarantees. So basically you have on the output of your neural network. So let's say you have your input is now, let's say a ball sent around a particular instance X, an infinity ball of radius epsilon. Now you want to basically control the output of your neural network, which it produces on this ball. And for this purpose, you basically derive upper and lower bounds for the output of each layer of the network, and then propagate it basically forward by this formula. So you get always the next upper bound and the next lower bound in this fashion using the upper and lower bounds of the previous layer. Okay, so while this technique gives actually super loose bounds, if you use it during training for, let's say, adversarial robustness on the in-distribution, then it yields currently one of the best guarantees for certified adversarial robustness, even though there exist actually much stronger techniques or much stronger bounds in the literature. But the fact is that if you use IBP during training, so use this bound during training, then this bound, even though it's loose, actually becomes tight for the network which you have trained on, and therefore it performs so well. Okay, so this is what we are now using, and we are, as I said, we want to have an upper bound on the confidence in a neighborhood around a given point. So here we just write the log of the confidence using the softmax function. One can write it like this, and the key is that now in this expression you just have differences of the logits, and this is exactly the form which you now can control using IBP. So we control this difference around in a neighborhood around a given point x using IBP. And this we then just plug in the formula for this confidence function, and then get an upper bound on the log confidence in the neighborhood in the infinity neighborhood of this given point x. Okay, and then you basically just plug this into this expression here, which has the effect that because this blows up in the initial phase of the training, so that's why we have here the logarithm, but then during training this becomes small, and that's why basically for small values it behaves more like a square. That's why we have proposed this term here. And then you just minimize your normal training loss and your upper bound on the confidence in this neighborhood of your out distribution samples during training. So this works very well, but in particular for this 80 million training image data set which we use as out distribution during training, the problem is that it contains actually a significant fraction of in-distribution images. And then basically these terms are contradicting each other, because this tries to enforce high confidence on in-distribution samples, and this tries then to enforce basically low confidence on these samples. And that leads clearly to a conflict, and then also deteriorates results. And therefore we have come up with this quantile version where we basically just produce on the easily distinguishable out distribution images then our upper bound, where we enforce this epsilon really uniform confidence in a whole neighborhood, whereas basically on the difficult ones where our bound is high, which are likely to be in distribution samples, we just don't enforce it just in a neighborhood, but just really just on the points itself. Okay, and this basically leads now really guarantees for the first guarantees. So here's again this running example. So on the in distribution it performs again well. On the out distribution it performs predicts low confidence. Also in a neighborhood predicts low confidence. But now the new feature is that you really have a provable guarantee in this neighborhood, so that you can say in a whole neighborhood, irrespectively of which image you will take, it produces confidence less than this 22% here. And so good is then the only method which can guarantee at the moment low confidence in a neighborhood around close out distribution images. Okay, so this was the part on out distribution detection. So now I want to switch gears a bit. So as I said, out distribution, we need this out distribution awareness basically in safe critical systems. On the other hand, as I want to show now, out distribution awareness leads also to better results for other problems where maybe safety critical or safety is not such a big issue. And the application I want to discuss now is semi-supervised learning. Yeah, semi-supervised learning came with the promise to deal with large amounts of unlabeled data. But in fact, most semi-supervised learning methods work with a closed world assumption. That means that they assume that all the unlabeled data comes actually from the in-distribution. But if you think about that you want to retrieve, let's say, a large amounts of images or text from the web, it will be clear that you cannot control that all these samples will be from the in-distribution. So that's why semi-supervised learning, at least if you want to really learn with large amounts of unlabeled data, in the wild, it will be from in and out distribution. So we really work in an open world setting. And the question we posed ourselves is that, can we leverage these large amounts of unlabeled data to improve classifiers? In particular, even when we have already a large data set, so for existing benchmark data sets. And the answer is yes. Even this most simple method like self-training is actually sufficient, but it has to be out-distribution aware. And let me quickly show how this out-distribution awareness works here. So this is a standard, this is a self-training scheme, and all the parts which are now specific for this out-distribution awareness are highlighted in blue. So basically the base teacher, there we use already basically outlier exposure for training. So we enforce uniform confidence on an out-distribution training samples. Then we calibrate the resulting teacher classifier on the in-distribution validation sets so that the pseudo labels which we produce are really calibrated. And then we select always in each round the top K unlabeled instances with highest confidence for each class. But we have so-called in and out distribution thresholds based on in and out distribution validation sets, which tell us how many samples we are allowed to take in order not to make basically a lot of errors in the samples which we add to our training set. And then we just produce the pseudo labels on the samples which we add. And on all the other instances which we don't add from the unlabeled data set, we produce here a mixture of uniform confidence and basically our predicted soft labels. So we basically still downweight the unlabeled instances which we do not think to be task relevant. And then you just repeat this process until the validation accuracy increases. And the interesting thing is that in the challenging setting now, where you have, let's say, just a small amount of labeled data, like here 4,000 labeled data for CIFAR 10, which is roughly 10% of the training set. Now the unlabeled data is then just the rest of the training images from CIFAR 10 plus respectively 1 million or 10 million unlabeled images from this 80 million tiny image data set. So the task relevant samples is really low in this case. And so it's really challenging because so there's a lot of potential to make errors when you add these samples to the training set. And in fact, all the or most of the established semi-supervised learning methods cannot deal with this setting, so they perform even worse than if you would just train here on the labeled data set, which is given here. But even established method for open world semi-supervised learning, which improve your performance. If you look now carefully what they actually select as samples internally, which is shown here at the bottom, you see actually that they think a lot of samples which are completely not task related, are actually added to the training set. And this poses really a problem for AI safety, because you basically have an inherent distribution shift, which you don't even notice when you just look at test performance. In contrast, our distribution aware self-training selects mostly just really samples which belong to this task and basically then also improves performance. And even more striking is that even now on benchmark data sets, so where it's actually quite difficult to still improve if you use the full data set of CIFAR 10, this out distribution where self-training can improve, here by 2% on CIFAR 10 and more than roughly 5% on CIFAR 100. And up to my knowledge, these are really also the best results which have been reported for this rather small architecture for ResNet 50. We have repeated this experiments also with larger architectures like a pyramid net, where we still get gains, but clearly the gains are then smaller than for the ResNet 50 architecture. Okay, with that I want to conclude. So I think this worst case adversarial perspective is really needed for out of distribution detection in safety critical systems, and we really need also guarantees there. Because reliable uncertainty estimates are essentially when we use machine learning in a scientific and industrial pipeline. And as I've shown, this out of distribution awareness is not just important in AI safety, but it's also important, for example, in this open world semi-supervised learning task. Regarding adversarial robustness, this is a common problem that often evaluations are bad, and therefore I just want to basically advertise here our outer attack suite, which is a completely parameter-free attack, and therefore and has been shown to be yield very reliable evaluation of adversarial robustness. yeah, with that, thanks a lot for your attention.
Thanks a lot for the very nice talk. Maybe I can start with one question from YouTube. So regarding RBF networks, what do you think of the idea of using kernels as activation functions to address extrapolation errors or overconfidence?
Yeah, this is a very good idea. Basically, the approach, which I did not have time to talk about, uses a Gaussian mixture model, which it integrates basically into the last layer. And this Gaussian mixture model allows us then actually control of the conditional distribution, and therefore we can actually then give this provable guarantee that the classifier produces low confidence far away from the training data. If you would just use an RBF network on the last layer, you could not directly prove this because you still have basically the network below you, below the last layer, which you cannot control. Yeah? So you need something which you can control. And that's why this is definitely a good approach and it will work nicely, but it's not, yeah, it will not give any provable guarantees.
Perfect. Thanks a lot. Maybe we can officially, oh, okay, Thomas Brox, please, one more question.
Yeah, I have a question because you're now enforcing that if you're far away from the training samples, you become uncertain. This is, of course, something that you not necessarily want. You also want to generalize. So if you're far away or a bit away from the samples, but maybe between two samples that belong to the same class, you maybe still want to be certain that you might be right there. So did you observe any drawbacks from your guarantees in classification and generalization?
No, actually, the nice thing is that this typically, if you train this outlier exposure, it performs even better than standard training. So you are not losing any performance. And having low confidence does not mean that your prediction is wrong, right? It just means that you flag that you are less certain about your prediction. And I think this is definitely a good feature if you think about whatever medical diagnosis systems and so on.
So you still assign the class label, it just has lower confidence than in the output.
Exactly.
Okay.
Perfect. So thanks a lot. Let's go into a 13-minute coffee break, and also, of course, internally, feel free to use the time for further discussions we couldn't have after the talks. Thanks.
Hello, salut und hallo. My name is Florian Bernhard and I will be chairing this session. So it's my great honor to introduce our next speaker, which is Thomas Brox, who will talk about fostering generalization in single view 3D reconstruction. The stage is yours.
Yeah, thanks. So I will present a work here which is about fostering generalization, and in particular in single view 3D reconstruction. That's an issue, as we'll see in a minute. So this is joint work with Bosch, and the line of work that we did here also dates back to some time when I worked with Intel Lab on that and Intel Labs on that problem. So in the past, since we have learned that you can use deep networks to map anything to anything, single view reconstruction has become very popular. So especially you can get nice depth map reconstructions from single images. So this is the work from Ranftel and colleagues, which also generalizes quite well to scenes because it was trained on a very large data set. So that's one strategy that you can use. But even then you see that there are some issues in small details. And then there's the other problem where you want to reconstruct full 3D shapes from the single images. And also that gives you nice reconstructions on first glance. But as we'll see, this only works more or less in distribution and not for new object classes. And the talk here will focus on this object shape reconstruction. So we were a bit skeptical when we got these nice results and everything looked nice, and we didn't really understand how the network does it. So we looked a bit deeper into that. Although you never know how networks do things, for sure we can at least get some indication of what might be going on. So what we did is we compared a couple of state-of-the-art reconstruction networks from that time. So this AtlasNet, then this OGN and Matryoshka networks. And we compared their behavior to some simple baselines that you know from pre-deep learning eras. Yeah, so this is just a baseline that is built on clustering the shapes, the training shapes, and then just representing each cluster by a mean shape. And then you could just train a classifier to classify from, given the single image, of which cluster it should be. Yeah, and then you get actually this result, and you see that it looks very similar to what you get with all these deep networks here. And what we also found that with some simple image retrieval, you actually get much nicer results than with all these networks. So the very classical way of just doing either image retrieval or then if you have the oracle, then you can also test shape retrieval. You get actually much better results than what you get here. So what you actually learn from this is that all these contemporary reconstruction networks, they mainly interpolate between mean shapes, and they don't really reconstruct any shape. And you're also seeing that from missing details, like, for example, the handles of the motorcycle. So what is the consequence of this? First of all, it gives you very little generalization to unseen shapes. So even if you provide the ground truth depth map, so actually the ambiguity from just the depth is no longer there because you provide the ground truth, even then reconstruction is poor if you test this on unseen shapes. Yeah, so here this was trained on lamps only, and then tested on motorcycles, and you see even though you know the ground truth depth map, you get a quite weird shape reconstruction. And what you also find is that the mean shape destroys all the details, as we have seen, like the handles of the motorcycle. So here's the problem that we want to look at. So given a training set with some depth map and shape pairs, yeah, for example, the depth map of some chairs and then the 3D shape of the chair, for some object classes, we want to find a 3D shape from a single view depth map on unseen shapes. Yeah, and so while the normal methods, they get some novel instances as test input and then want to produce the shape for that, we actually want to do this for novel classes, so unseen classes. And that follows also the earlier work of Genre, which already set up something like that on object classes. What we added to that is also new arrangements of objects. So for example, having two chairs next to each other, or a sofa and a table, and all these combinations. And especially these new object arrangements also show quite well that there is an issue in the way on how these reconstruction networks currently solve the problem. Because even if you train on the same object class, so in this case chair, and you provide the ground truth depth map, you don't get a reasonable reconstruction of these two chairs. Yeah? So even then, the generalization does not work to the new arrangements. It's just because the learned global prior dominates everything. So it has just seen single chairs and not two chairs, and that's why it always will produce a single chair. And if it's two chairs, then we'll just make a bench out of it. And so that's why this object arrangement setting showcases this problem quite well. And what it also shows is actually the importance of recombination, which goes also a bit beyond this particular problem of single view 3D reconstruction. If you don't reuse partial information, that means that a network must see all possible combinations during training. Yeah, so in the case of the two chairs, even if you have seen two chairs during training next to each other, if you then move one chair, it's a new configuration. And if you want to generalize to that, you also have to see this configuration if your method cannot recombine the partial information. And you can think a little bit of why convolutional networks actually work, because there is some recombination going on at the patch level. And the ability to recombine is actually a prerequisite for generalization, because it replaces the exponential scaling in the number of training samples to a linear scaling. And it seems that the training setup that we have here in this single view 3D reconstruction does not foster learning of local shape priors at all. And that means there's nothing that can be recombined. So now that we know the problem, it's relatively easy to fix it. So the idea is that you train network to reconstruct, rather than the full object, local blocks. Yeah, so you can just take local blocks from your input image and then reconstruct the 3D blocks with a network, just like you do that for the global shape. Yeah, and then you can build together the whole object, or also a whole scene, as a combination of the local reconstructions. And you see that this works pretty well, and even gets you some relatively nice smooth shapes with quite many details. Of course, there is an issue with that. The downside of this local reconstruction is that you're missing global consistency. So on the visible side of the object, that's still okay, because there we had all the depth information, so reconstruction is quite good already. But on the invisible side of the object, you see that the different local priors, they are not consistent, so they don't agree with each other, and that's why you get a relatively weird shape surface there. So you can fix this by applying a global prior, and what we do here is actually simply a multi-scale ensemble. So instead of just having one block size that we consider, we actually consider multiple of those, so smaller ones, bigger ones, and then also the global shape. And for each of them, we train a small network that does the reconstruction at that patch level, and then we just sum up the results to get a final global shape. And with that, you see that you would get different reconstructions from these different networks, and the combination then gets you typically the best of both worlds. And you can now test on how well this works and compare this to the global priors that are typically used. So this is now trained on 3 different classes: chairs, planes, and cars. And then you provide a lamp as input. And yeah, you see with the global prior, the network is completely confused because it doesn't fit to any global prior that it knows. And you just get this, this bubble here. Whereas if you combine the local and global priors, then you get a reasonable reconstruction. Of course, it looks better from the visible side than from the invisible one, because you have the ground truth depth map here as input. So it's easier there. But yeah, the overall reconstruction is reasonable. And here's an example of training only on chairs, and then just showing chairs, but in an arrangement of 2 chairs. And whereas the global prior again converts this into a fancy single chair that doesn't look very reasonable, you get a very nice reconstruction with the global and global priors together. You can also cover this in numbers. So we compare here this global network, so occupancy networks, that is our baseline that we also use for our hierarchical prior networks. So that's the global prior. Then there is another work that recently came, which also uses some local implicit functions, but they don't enforce the learning a local prior, and that's why they cannot really benefit from the locality. So the recombination doesn't work at the prior level. And we have here in the red part here the setting where you trained on chairs, airplanes, and cars. And you see on the unseen objects, so this is all an F score. So this metric that is typically used here for comparing the quality of the shapes. And you see there's a large improvement if you use these hierarchical prior networks, both for unseen object and for the object compositions, especially for the object compositions, the gap is even larger. And if you only train on lamps, then you also see that the difference is actually not that large anymore. So thanks to these local priors, you actually don't need all these different classes to get a reasonable reconstruction. But of course, you also benefit from the global prior. So if you're in distribution, so if you have a global prior of the actual object, then of course, on the invisible side, you will get a better reconstruction than if you don't have that. Yeah, but even if you don't see the object at all, you get a reasonable reconstruction now. We also tested this on some real-world depth maps, so not only the ground truth ones, although that was not the focus of our work initially. You see that also here, you can get some reasonable results, although here, of course, there's very little information in the depth map and in the prior because it hasn't seen the object class before and it hasn't seen and the depth map is incomplete. So of course, then also the reconstruction is limited, but it makes some sense. One thing that I want to highlight also is that the locality improves the data efficiency quite dramatically. So if you compare here the global prior network and here the local one with a patch size of 64, and this is at the log scale, then you see that already with 1% of the training samples, the local network actually flattens out. So it has seen enough data to do its job. This is just because, first of all, it enables the recombination. So that means you anyway generalize better. So you need fewer training samples. And secondly, also because you're cutting out these small patches, you actually increase the effective training set size. Yeah? Because of these local blocks, you have multiple of these blocks in a shape. So you can effectively more data than if you only have one sample per image. Okay, so to summarize, I highlighted that the ability to recombine is key for generalization. This holds true on all the tasks, but it's particularly evident here on this single view reconstruction. And we have seen that locality in single view reconstruction enables this recombination. And locality also requires much fewer training samples for two reasons, mainly this better generalization due to the recombination, but also because we effectively have a larger training set size. Thank you very much.
Okay, thank you very much, Thomas, for this nice presentation. So I think we have plenty of time for questions. Are there any questions? Okay, there's a question by Christian Kersting.
Yeah, so coming back, so thanks for the talk. Coming back to the argument from yesterday, saying that we don't just need world knowledge, but world models. Is this work also showing that we should not just talk about models, but maybe use knowledge to combine priors, local priors on the fly, so that this might be the glue between the different models that we may have to combine at some point? Does that make sense, or should it be the whole models?
Yeah, so I'm not sure if I on the same page already, but so if you want to model the world, since the world is complex, you cannot do without recombination. So that means you cannot build a global world model prior. In that sense, this work also fits in there, yeah. So because you actually have to decompose the world into recombinable parts, learn those, and then also learn how they have to be combined to make models that you have seen, yeah, or that make sense. So in that sense, you have to bring the local recombinable parts together with the global knowledge.
Yeah, and I was wondering, I mean, it's a lot about
one of the challenges.
It's a lot about inductive biases that we have to capture somehow, right? And seems like the inductive biases are maybe a lot driven by local priors. And I was wondering how much this can give us some form of modularity already, without already trying to combine arbitrary models, and maybe the priors are a bit like the interface layer that is much easier to handle. I mean, super high level, I agree. I mean, nothing concrete now, but.
Yeah, the inductive bias sometimes is, it's not clear what the inductive bias of a network architecture or actually also of a training scheme is. Yeah, so because the architecture here, it's typically an encoder-decoder architecture. So from that point of view, there would be the way, it would be possible to recombine. Yeah, so there's no point. It's just that because of the training setup that you always learn from these global shapes, there is no fostering of this recombination and learning of local priors. So that's why you have to consider actually both the inductive bias of the architecture and the inductive bias of your training setup. And often the training setup is more important than the architecture, because what we see actually does, meanwhile, that you can use whatever architecture, if it's not completely dumb, it will work. It's more about how you formulate the learning task, whether it will give you something reasonable or not. And in this case, it was definitely the learning task setup that was not right, because as a network, we actually used the same architecture as the others. Yeah, so we didn't change anything there.
Thanks.
Okay, there's also a question from YouTube. I'm just reading it. How about having some data fidelity term? For example, there should be a projection of the mesh which matches the depth map. I guess similar to what was proposed for image reconstruction by Michael Möller.
Yeah, so in this field of depth reconstruction, there were also some reprojection-based methods that reproject the 3D shape to the image and then can argue in the image space. So we have also played a little bit with that, and there, of course, you get some direct feedback whether your reconstruction makes sense or not on the training data. But again, on the training data, the things work, so your reprojection error will also be small. So in that sense, it doesn't help. It only helps if you, it doesn't help you on new test samples, because there you don't have the relationship. Does that make sense? I know, you know the depth map, yeah. So if you project back, you would see in the depth map that it doesn't work. But during training, that would just make sure that your depth map projection is consistent, but it wouldn't help you in the invisible parts.
There's also another question on YouTube asking, what is the difference of your work and the work PatchNets from ICCV 2020?
So the difference is that we really enforce learning these local priors. Yeah, so there have been a couple of works that do that use some locality in the representation. So also this other work that I mentioned here. This one from Genova, that is CVPR 2020. They also used local functions, but they didn't enforce the learning of the local priors, and that's why they cannot actually perform better on the unseen objects. So again, from the representation setup, everything is fine, but not from the training setup.
Okay, and one more last question from YouTube. How does the query time of your approach to reconstruct an object from a depth field compare to the vanilla ONet?
So runtime is, well, because you have multiple networks, it scales by the number of networks that you have in the ensemble. Potentially, you can make these networks a little bit smaller because, yeah, you have multiple of those, especially those here that only reconstruct local patches can be probably smaller. Yeah, so currently we use the same network everywhere, so there it's just a linear scaling with the number of networks that we use.
Okay, thank you very much for the nice discussion. We should now move on to the next speaker, who will be Julien Mayral. Can you please start sharing your screen?
Yes, I can. Just okay, so you should see it now.
Okay, great. So Julien will talk about Lucas Canade Reloaded, end-to-end super resolution from raw image burst. The stage is yours.
Well, thank you. So first, thank you very much for organizing this very nice workshop. So I'm going to talk about super resolution, and more precisely, we are going to use the Lucas Canade algorithm, which was invented about 40 years ago to align two images. So if you are from computer vision, you should probably know about this algorithm, because we can probably say that it was for a long time one of the very few computer vision algorithms that was actually working in the real life. And before I go further, I would like simply to show you a picture of my collaborators, because this was in fact the work of my PhD student, Bruno LeCun. Can you see the, yes, okay, there is a small delay. So this is the work of my PhD student, Bruno LeCun, who is co-advised with Jean Bons. And to explain more precisely what we want to do here, I'm going to do as in live science papers, which is to start with some results. And so here, this is a picture that was taken using a Panasonic camera. And our goal is simply, given a scene like that, to be able to zoom on the small squares and increase the quality of what we see here. Now, what you don't see at the moment is that when you zoom, we see that in fact this picture was taken with a low exposure time. So that means that the signal is pretty weak. It has to be amplified to reconstruct a color image. And when you amplify a signal, you also amplify the noise, such that the camera has to work very hard to remove the noise, reconstruct the color image from the raw sensor data, and it will lose lots of information in the process. So this is here the output of the camera. But if instead you are able to take multiple frames of the same scene and combine the information from the burst, this is the types of results that we get, which I hope will appear nicely on your screen if Zoom does not add compression artifacts. So here, I simply take my camera, I press the shutter, and instead of taking a single scene, I will take 30 frames. And by combining information from these frames, I recover lots of nice information. For example, here, you can see lots of tiny details that were impossible to get from a single image. So another result here. So on this other part of the picture, we can also recover very fine details, such as the hair of Elsa, and also some parts of the picture were overexposed. We can also recover some information. Now, the last example before I proceed with the method is it's another part of the scene. So I like this one very much, not because it uses a bottle of rum. So I'm not a big fan of using alcohol for scientific presentation, but from an image processing point of view, it's a very interesting image that contains lots of very fine details that are very hard to recover. If you look at the output of the camera on the left, it's impossible to read anything. Okay, so before I present the method, it's important to mention that here we are working with the raw data from the sensor. And if you are not familiar with how a camera processes sensor data, I will give a very simplified view. So basically, there is the first thing to know about sensor data is that for each pixel, you don't get the full color information. There are tiny, small colored filters in front of every pixel, organized on a particular pattern called the Bayer pattern. represented here by this sequence of green, red pixels, then blue, green. And the task of reconstructing a color image from this partial information. So it's already an inverse problem where you need to interpolate. This task is called demosaicing. And because the sensor data is very noisy, then we need also to denoise. So if we are going to combine information from multiple frames, working with raw data is in fact very important. Why? Because like I showed you before, the camera image signal processing unit, which does its best, is losing lots of information. Now, working with raw data has also another advantage, which is that we can leverage aliasing. And I don't know if you see the picture yet, but aliasing is a very basic phenomenon from signal processing, which says that if you have a high frequency signal and you undersample it because your sensor has a specific resolution, you're not going to see these high frequencies. What you are going to see is some low frequency artifacts. And this is something that appears in the real life. For example, on the right, you should see a burst of images. And there is a very high frequencies in this signal, such that you see some bluish or orangish artifacts. So this is typically aliasing. So if you deal with a single image, aliasing is bad. It's known as something bad. And it is so bad that, in fact, on many cameras, there is an optical filter in front of the sensor that will remove high frequencies. So typically, we don't like these types of filters. Now, if we deal with multiple frames, aliasing is in fact something good. And it is something which is well known by people who have actually worked on this topic. And intuitively, it's very simple. What is aliasing? It's nothing else than a measurement of high frequencies. And if you have multiple measurements, then there is hope to recover the true signal. So our goal will be to exploit these types of high frequencies hidden in the data, combine information from multiple frames to reconstruct a high resolution image. So this task is in fact pretty hard for several reasons. One of them is that we take the picture by hand, by taking the camera by hand, and there is motion. There is hand motion that we need to take care of. That means that we need to align these images with sub-pixel accuracy. Then you also need to deal with noisy data, such that you need to do blind denoising in your case, meaning that you have some amount of noise. You don't even know how much noise you have to deal with it. We have also to reconstruct color images from the Bayer pattern. We have to do demosaicing. And on top of this, we want to do super resolution. So there are lots of prior work on super resolution. So I don't want to do a survey for this short presentation. I'm going simply to mention this nice paper by ETH, Bat et al., which adopts a deep learning method. And when you think about it, applying a deep learning model for this task is actually a bit complicated. And one of the reasons is that from an experimental point of view, it's actually impossible to acquire very high quality training data, meaning it's actually impossible to take at the same time a high quality, high resolution color image and low resolution raw frames, a burst of raw frames. And why is that? Simply because there will be always misalignments between the ground truth and the raw frames. Nevertheless, there is also a very nice protocol in this paper that is using quite realistic way of generating synthetic raw data from high quality color images. And we are going to benefit from this work. Now, something that will sound familiar, given the discussion of yesterday, given the talk of Michael Müller, is that we are going to start by looking at the problem from the old world point of view of classical inverse problems, meaning that we simply consider the way the data is generated. So for example, take a high quality color image X. We are going to assume that the burst that we observe, the raw data, is generated from X by applying a sequence of operators and by adding some noise. And so these different operators are the following ones. You have WPK, which is a warping operator that is, in your case, an affine transformation of pixel coordinates parameterized by 6 parameters. And this model is in fact pretty good if we deal to model hand motion, if you are only interested in local crops, in zooming on small parts of the image. So after you do your warping operator, we need to reduce the resolution. So both spatially and also in the spectral domain because of the Bayer pattern, such that you have an integrator B plus a subsampling operator D. So after you have this image formation model, it's becoming very natural to formulate it as an inverse problem where you want to minimize this cost function with respect to X, with respect to the motion parameter. And because the problem is not necessarily well posed, you also need a good image prior. For example, here in the old world, we may use total variation. And then you optimize. So there are plenty of ways of optimizing this. We are going to choose a very simple approach, which is a penalty method that consists of introducing an auxiliary variable z, which has to be as close as possible to x. So we have a quadratic term here with a parameter mu t, which is going to increase along the iteration such that when we proceed, z becomes closer and closer to x. So why we do that? Simply because after doing this, it's becoming very natural to use a block coordinate descent approach to minimize the objective. And here comes the first interesting fact, which is that if you fix x and z, and you minimize with respect to pk using a Gauss-Newton algorithm, then you recover the Lucas-Canaday algorithm from 1981. And in fact, I should say that Lucas-Canaday is not only Gauss-Newton, it's also the result of a huge engineering effort, which is extremely useful for us. There are lots of implementation tricks that make it robust and fast. So now when we look at the other variables, if we minimize with respect to x, it requires computing the proximal operator of the prior phi theta. If I'm minimizing with respect to z, it's a simple quadratic functions. There are plenty of ways to do that. In our case, we will simply do very basic gradient descent steps. And mu t increases over the iterations. So the advantage is the robustness of this approach and the interpretability. It solves what it is supposed to solve. If we change the types of data, it will still solve the same problem. The drawback is that designing a good image prior by hand, it's actually very hard. So here comes then the new world of deep learning models, where we encode a form of prior knowledge in the model architecture. For example, if you use a convolutional neural network, you implicitly assume that there is some local stationarity in images at multiple scales. And this gives us the ability to train the model parameters theta end to end if we have training data. And very often for inverse problems, once you have the right model, the right setup, the right data, you achieve state-of-the-art results. So this is adaptive to the task. And one of the drawbacks we have heard about this already is that you learn a model which is tuned to a specific data distribution. When you go out of this distribution, bad things can happen. So now bridging the two worlds together, we have seen already that in a previous presentation. Well, there is one thing we are going to do is to adopt the classical point of view of inverse problems. And the first thing we do is that we are going to replace the proximal operator by a parametric function, which is good to remove artifacts. And for that, we use a convolutional neural network. Now, why does it make sense to replace a proximal operator by such a parametric function? There is one reason, which is just intuition. So what is the intuition is that the proximal operator, its role is to remove artifacts. It takes as input z, it provides x, which is closer to what a natural image should be. Then the other thing that could justify this is that from an optimization point of view, many of the optimization proofs for these optimization methods in a non-convex setup, they only require the proximal operator to be non-expansive to converge. And this is something we can also do using a convnet. We can constrain the weights such that the convnet is also non-expansive. So I'm not claiming that this is something we did here in this work. The second idea is the idea of unrolled optimization. So we consider the previous block coordinate descent approach, which at iteration t produces an estimate x hat t, given an input burst of low resolution frames. And if we see this estimate after t steps as a sequence of operations that may be differentiable, we can simply use backpropagation and train the model parameters to minimize the reconstruction loss. For example, here, assuming that now we have training data, pairs of high quality color images xi and robust yi, we can simply minimize the loss such that our estimates match the ground truth data. So this is now just a very basic view of our method. We can see it as an architecture that can be coded in PyTorch or TensorFlow or whatever deep learning framework that does steps that are interpretable. It will alternate between estimation data fitting, basically optimizing with respect to z, denoising by using a convnet, and Lucas Canale steps that will refine the motion estimation between the different frames. So it has some interpretability, and now we benefit from a data-driven image prior because we are going to learn the weights of the CNN in a supervised fashion. So I already showed you some results about this, this approach. Let me show you now something not very realistic, but a bit extreme, just to see what these types of approach can produce. So here in the next experiment, we consider RGB images, not raw images, and we generate a burst of low resolution frames of 20 frames with random affine motions that we don't know at test time. So we apply our method, which has this classical point of view of classical inverse problems. And this is the types of results that we can get if we simply ask to increase the resolution by 16. So it's not something you are going to be able to do in the real life, but I think it's still interesting to see as a proof of concept what we can get. Now, the first results in the presentations were obtained using real data, using a Panasonic camera, which did not have, by the way, an anti-aliasing filter. We tried it on several other types of cameras, also on smartphones. And here, the next result is obtained using a Pixel 4a camera. So on the left, we have the picture that was taken in the street without using just default setting for the camera. And we are going to zoom on this very tiny red square. If we do that, in the middle, this is what the smartphone produces. But if we take a burst and you are able to process the data which is contained in the burst, on the right, this is what we obtain. So the next example, I like it very much. It's also a picture that was taken using the Pixel 4a camera. The small red square is very, very tiny. And what I like in this picture is that we have some elements with very high frequencies, and we clearly see some aliasing artifacts. In the middle, you see this blue and orange artifacts. And on the right, this is what we recover by processing a burst of 30 frames. So we are relatively excited about these types of results because it's basically working in the real life. Now, of course, there are some failure cases. And the most important one is that so far, we assume that the scenes are static. That means that if there is a moving object, we are going to have a mismatch between the model and the way the data is produced. And for example, on the bottom right, we have a guy running and there is a ghosting artifact simply because the images are not well aligned. We use simply an affine motion model, which is not realistic for these types of scenes. So it's a bit hard to see probably on Zoom, but these are on the left other types of artifacts that will appear when there is some mismatch with, between the model and the data. So as a take-home message, there are several ones. Well, there is one which is that 40 years old computer vision algorithms are useful. You should be convinced about that if you are using convnets, by the way. One which is well known in signal processing is that aliasing can be good if we deal with multiple frames. And something, and I'm not the only ones to say that, is that classical approaches are robust and interpretable, and they greatly benefit from deep learning principles, which are here differentiable programming. And I will now stop here, and I will be happy to answer any question.
Okay, thank you very much for the great talk. Do we have any questions? So it seems so far there are no questions on YouTube. Maybe let me ask a quick question. What do you think will be required to also handle dynamic scenes in contrast to only static scenes? What do you think, what machinery will be necessary to successfully deal with these cases?
So it's a good question. So we are, at some point we'll need to have, I mean, it will simply mean that we need to have an optical, I mean, to model the optical flow in the scene. And what is the right machinery? It's something that we are currently investigating. One of the difficulties that we really need to align with sub-pixel accuracy. And if we simply use an optical flow solver as a black box, it's probably not going to work immediately. But we are working on it, and it will be a challenging task indeed to do that.
Okay. Let's have a last final question, a short question by Klaus Müller.
Yeah, so I'm wondering, very nice talk and impressive results. So I'm wondering whether, if you think about video coding, then that you could, I mean, video coding tries to compress the movements, and it has some information on how these movements are. So the question is whether this could be used for your purpose in order to get rid of ghosts.
So basically, I mean, it's a bit a chicken and egg problem, because if we are able to model right the motion, we will be able also to improve the coding part. Now, something I should mention as well is that this problem is actually different from video super resolution. And the reason is that we are dealing with raw frames. And typically in videos, we are already working with the output of the device, of the camera. And the problem is actually quite of a different nature. So the alignment, I agree, can be useful. The motion, if we have a perfect idea about the motion in the scene, then we can apply your method. But dealing with videos, it's actually a slightly different problem because of this, the fact that we deal with raw images, raw data.
Okay, in consideration of time, let's move on to the last speaker of this session, who will be Daniel Kremers.
Thank you, Florian, for chairing the session. It's my pleasure to be here as well. I want to talk about visual SLAM in the age of self-supervised learning. And this is trying to combine research in simultaneous localization and mapping with recent developments in deep learning. The work that I'm presenting has been done mostly by current and former students of mine, in particular Nan, Lucas, Rui, and Jacob. Visual SLAM is a classical problem. It has a long history. In fact, more than 100 years, which for computer vision is very long. And so back in the days, there were applied mathematicians like Krupa who proved theorems of the type that if you observe 5 corresponding points in 2 images, you can actually recover the relative motion of the camera and the 3D location of these points. And whereas originally this was done on aerial images and manually in the 70s, 80s, and 90s, the computer vision community set out to deploy computers to actually do these reconstructions. And they followed very closely in Krupa's footsteps and developed quite impressive techniques. And some of the first real-time capable visual SLAM techniques emerged around 2000. This is just a few representative works in this field. And what's important, though, is that most of these approaches actually do follow very closely in Krupa's footsteps. That means they start with 2 images, because Krupa said we assume 2 images. They extract points, because Krupa said we want points. And then they need to identify correspondences, because Krupa said we need corresponding point pairs. And once you have corresponding point pairs, you can run algorithms such as bundle adjustment that minimize this reprojection error to compute 3D structure and camera motion. And this is a very sophisticated pipeline by now. Nevertheless, I think it's always important to question even the pioneers. And I would argue Krupa may have been very pioneering, but I think to real-time SLAM and real-time structure from motion, he may have also been quite misleading. The reason is the following. When you take a camera nowadays and you switch it on, you don't see points, you see colors or brightness values. And in particular, you don't have corresponding points. And we all know that estimating correspondence is one of the most challenging and nasty problems in vision. And in some sense, any error you make in that first abstraction step of points and corresponding points, those errors are going to propagate and deteriorate your solution, right? And you can typically not recover unless you add heuristics such as ransack to resample the correspondences, etc. And so I think it's time to revisit this paradigm and see, can we not get directly from the sensory measurements to a 3D reconstruction in terms of camera motion and 3D structure? And this is an approach that we advocate and we refer to as direct, because it goes straight from the sensory data to your estimates. And I think anyone who works in sensor analysis, let's say if you work in a Bayesian framework, etc., you will agree that the closer you stick to your sensory measurements, the more likely you will actually achieve optimal solutions, right? Say, getting the best reconstruction, the best camera motion given your sensory data. But the key difference between what we call these classical key point-based methods on the left and the direct methods on the right is that the key point methods minimize a geometric reprojection error, like in bundle adjustment, whereas the direct methods minimize a photometric color consistency error. So you're basically saying, find a camera motion and a 3D world such that when I project my points into 3D and back out into the other images, I should get consistency. So it is that brightness consistency that drives everything, much like in optical flow that served as inspiration here. But more specifically, let's look at one of these approaches, a technique we called LSD SLAM for large-scale direct SLAM. It's a somewhat sophisticated approach. It starts on the top left with the input video stream, and then there's a tracking and a mapping component that run in alternation. And if we look at this tracking component here that tracks the rigid body motion of the camera, here you see the brightness consistency as a loss function. So we have a keyframe, we have a current frame, and we basically try to align the current frame to the keyframe in terms of the brightness consistency. And so all the pixels X contribute here to that measure of brightness consistency. But since we only estimate the 6 parameters of the rigid body motion GXI, this can be easily done in a coarse-to-fine hierarchical scheme on a single core of a CPU in real time. So this is very fast to compute. And so we can use a simple CPU even on a laptop here, and we can track the camera in real time, as you see here. And on the right, you see the tracked camera and the 3D structure of the world emerging. We called it LSD SLAM for large-scale direct SLAM because among real-time capable visual SLAM methods, it was one of the first that allowed to really reconstruct, as you see here, fairly large environments with almost no distortion. And in fact, this challenge has driven us a lot over the last years. How do we minimize the drift? Here's a follow-up work called direct sparse odometry, where we actually more jointly estimate camera motion and 3D structure in a Gauss-Newton optimization framework. And top left, you see the images. You see the method. It runs in real time and tracks the camera motion at very high precision and maps the environment in real time. And as you can see, we can walk through the subway station. And of course, there's going to be errors in the camera pose that will accumulate over thousands of frames. But what is this total error here, the drift? You see the bicycle on the top left is actually reconstructed twice. And the drift here is what, 2 meters, maybe 2 or 3 meters on a distance of hundreds of meters of walking. So you could say the drift is less than, say, 1%. But how do we quantify this? So here's how we went about this. One of the biggest challenges, especially in the deep learning age nowadays, is how do we get ground truth? How do we quantify performance of methods? We took the camera outside, we recorded, and inside all sorts of different lenses, different cameras, different motions, different environments. They're very different sequences, but they all have one thing in common. They all loop back to where we started from. And that allows us to compute a total drift per sequence. And this is what we plot here in this kind of statistical quantitative evaluation and compare to what was considered the state of the art in key point-based methods in ORB-SLAM, a very powerful and popular technique from a team in Zaragoza. What you see here is plotted is the translational, the rotational, and the scale error always, and on the y-axis, the number of sequences where we achieve that error. So ultimately, you want to be in the top left corner. Dashed is the real-time method, solid line at the time, 2017 or so. Solid is if you have a bit more compute time, you get a slightly higher precision. And you can read these plots in many ways. For example, you can say, what is the best, the precision on the best 300 runs here? ORB-SLAM has a precision of 6 and DSO has a precision of an error of 1. So the error is reduced by almost an order of magnitude here. So this is a quite dramatic improvement that I believe comes from modeling the raw sensory data and going straight to the estimates of 3D structure and camera motion. Or you can say, if you want robustness, let's say in an application, you want to impose maximum error of 2. How many sequences of the 500 can we track with that error? Whereas the state of the art can track 100, we can track 400 of the 500 sequences. So a dramatic boost in robustness as well. Now the key question is, how can I further boost the precision of such systems with the deep networks? And we've seen over the last years, deep nets had a huge impact in virtually all areas of computer vision and beyond. But 3D reconstruction, Thomas Brox talked about it, remains, I think, one of the challenging areas. There has been quite a number of approaches that employ deep networks for visual SLAM or structure from motion, as it used to be called. But unfortunately, a lot of these techniques, when it comes to precision of camera tracking, do not achieve state-of-the-art performance. They show you can use deep nets, you can train them to do this task, but they don't seem to perform very well compared to what we had before. I don't, want to go too much into detail why that is, but what we've been advocating somehow is how can we combine the best of both worlds? Because if you do an end-to-end training of a deep network, you lose a lot of the knowledge about how cameras move, about the perspective projection into images that right? But there is a lot you can do with deep networks. For example, it turns out you can train a network to, just given a single image, predict the depths of the scene. And that is quite impressive, but not surprising, because even we as humans, if we see photographs like that, we can estimate how far things are from the camera. Turns out we can further improve the precision of these networks. This is Nanyang's work from 2018. So we get fairly accurate depth predictions for single images, for keyframes, if you will. Now we can feed these predictions into our SLAM approach. In terms of a loss function that we add to the SLAM approach, where we say find a reconstruction that is maximally consistent with these depth predictions. And once we do that, this is what we get. So what you see here now is a reconstruction from just one single moving camera. So it's not using stereo, it's not using inertial, it's not using GPS. It just uses the bottom left video to reconstruct, as you can see, the world on a very large scale. And it's essentially drift-free. So even if you drive around the block, as you see here, there's practically no drift, especially compared to the standard monocular approach. In particular, we actually get scaled reconstructions of the world. We get the metric scale. Why? Because the depth predictions are in metric scale. Here's a comparison to state-of-the-art stereo methods, and it turns out this proposed deep learning enhanced method outperforms some of the state-of-the-art stereo-based methods, even though it uses only one single camera. And so in some sense, the message here is that by feeding in predictions from a deep network, we can compensate for missing sensory information. Turns out we can go further. This is from last year, D3VO, so deep depths, deep pose, and deep uncertainty. We can not only predict depths, but something that was earlier also shown in Thomas Brock's lab, you can estimate with deep networks, you can train them to predict the relative motion of the camera given 2 consecutive frames. And we can predict some notion of uncertainty. Let me go into more details. So, you know, I said color consistency is what drives everything. What we are doing now really is we deploy deep networks to help us understand how colors really vary from one image to the other, right? These are things we can try to manually model, but we can also try to use deep networks to learn that from examples. Typically, for example, brightness is not preserved, right? If you take 2 consecutive images, you have aperture changes. And so you can actually model an affine brightness transformation to align the 2 images. And you can train a deep network given the 2 images to predict that affine transformation that aligns them in terms of brightness. But even then, if you go to the real world, you have structures here in the real world, you know, metallic structures, glass windows, where brightness will not be preserved no matter what you align, right? So then we can train a deep network to predict what's often called aleatoric uncertainty. So it can tell us where in the image does it think brightness will or will not be preserved. And we can simply downweight these loss functions here that use this color consistency in a self-supervised manner to downweight those areas where brightness is likely not preserved. And it turns out that works really well and actually generalizes to different data sets. Now we fuse all of these predictions, as I said, into the loss function to make sure everything is consistent. And then we can look at how good are we in terms of predicting the depths. And it turns out here's a comparison to different methods on Kitty and on UROC. And we show compared to the state-of-the-art monodepths 2, we get a significant improvement in depth prediction. And what's nice is this generalizes to other data sets. So we train on, say, Kitty here, and we deploy it in the cityscapes data set. And both the depth prediction, but also this uncertainty prediction works fairly reliably to tell us here we expect in the windows, for example, the brightness will not be preserved. Now, coming back to estimating the camera precision, the odometry is often called, here is a comparison to classical and to deep learning-based methods, and it shows that we can do better than state-of-the-art stereo methods, again. But even more, we can compare to state-of-the-art stereo inertial methods, and we show that this monocular method is on par with the leading stereo inertial methods, even though it uses only one single camera. So this is how you can boost the precision of SLAM methods with deep networks. Of course, you can do much more with deep networks. This is work supported by the company Artisense that I co-founded. They develop multi-sensor systems that they can deploy in a whole fleet of cars here in a project in Berlin. And you can see we can get semantic reconstructions where we can label drivable areas, sidewalk, cars, pedestrians, etc. And we can, in pretty much no time with very low-cost hardware, create large-scale semantic 3D maps of the world we live in. And I think this is very valuable for autonomous driving to have maps and semantics. And going further, we can use multiple consecutive images and train networks to predict dense, detailed maps of the world, as this one, computed from only one single moving camera. And I think this is again important because you see we're now at a level where we can really drop the LiDAR from the self-driving cars, because with just one camera, we can get extremely dense and detailed colored reconstructions of the world, right? And this, I think, is a perfect test bed for training self-driving cars, for example, because you can simply create copies of the 3D world just by driving through them with a single camera. That's all I wanted to talk about. Thank you for your attention.
Thank you very much for the nice presentation, Daniel. So I think there's a bit of time for questions. So there's one question from YouTube. Are there any approaches, experiments, or results performed of time-invariant visual SLAM, for example, using similar as with superpoint or superglue for day-night points matching?
That's a complex question. Time-invariant, SLAM, day-night. Let me try to address some of the topics in the question. So yes, one of the key challenges that artisans has been focusing on a lot is extending the performance of these methods to corner cases. And this is often when you take something from the research lab and try to deploy it in the real world. One of the biggest challenges is to make sure that the corner cases get eliminated, that you can guarantee performance even in low light conditions, in rain, in snow, in the dark, etc. And this, to some extent, there is a challenge in tweaking the algorithms to work reliably, but there's a lot we can do, and we found a dramatic boost in performance by deploying deep networks to help us understand the color and brightness variations and how they vary with the seasons, with the lighting, etc. And so we've shown that there is a technique called a GN-net, we call it Gauss-Newton net, that allows us to cope with quite significant variations in color, brightness, with low light conditions, with rain and snow, etc.
Okay, thank you. I think in consideration of time, we should close this session, and I would like to thank everyone for attending. Now we will have our lunch break, which will be roughly 1 hour, and we will reconvene at 1:30 with Eric Moulin's talk. See you later.
Thank you.
Welcome back, everyone, to the French-German Machine Learning Symposium. My name is Nicolas Demmel, and I will be chairing this session. I'm very happy to announce our first speaker, Eric Moline, who will be talking on non-equilibrium sampling. Eric, please take it away.
Thanks a lot. Okay, so it's a joint work with Achille Tin, who is a PhD student of mine. So I co-advise the student with Arnaud Doucet, who is a professor at University of Oxford and also a worker at DeepMind, so working in DeepMind in London, and myself. So there are also a contribution from others in this talk. Okay, so just a brief recap of what I'm doing. So what I'm trying to pretend today is that there are many problems in machine learning and artificial intelligence that involve inference of probability distribution. And in many cases, I've explained why this probability distribution are known to a normalizing constant. So of course, the problem is not new. So it's at the core of many developments, particularly, and it's a main problem in Bayesian inference, and in particular for uncertainty quantification. So I'm working on this topic, but I will not explain much in this area. And now it appears also in generative models, in particular in variational autoencoders. I will explain why generative adversarial networks. So Gerard Bio will speak about that. And also there are other issues which are of interest, like missing data, that I will not speak about that. Okay, so each of these problems comes with its own flavors, but all these problems involve basically the problem of sampling, so the ability to produce samples from complex probability distribution. So the second problem is problem of computation of normalizing constants, so which is called for example, in Bayesian inference, it will be called evidence, and it will be interesting when you are willing to compare, for example, from Bayesian point of view, different models in other domains, like in statistical physics, it's called free energy computation, which are very important. And of course, for Bayesian inference, you have also to compute posterior means. Well, today I will focus on working more or less on all of this topic for for 30 years now. But today we focus on generative models. So what is a generative model? So there are many sorts of generative models, but so there have been a considerable interest right now, which have been more or less triggered by the early work of, among many others, I would say, by Max Weding and his student Kingma, and also Rezende. So, and there are many people which are working on this area now. And what is a generative model? So I will mostly consider in this talk the deep latent Gaussian model, but there are many different types of generative models. So what are the assumptions? So basically in all this model, you have a latent space, which is typically of low dimension compared to the high dimension of the observation. And this latent space can have a simple structure. So it's not so true right now if you look at the last generation of VQ-VIE, for example, where the latent space has very complex structure. But in deep latent Gaussian models, it has a very simple structure. And the complexity comes from feeding this low dimensional simple latent variable into a deep neural net, and then adding at the output of the network some noise. Okay, so it's if you want to see how it works, so you have a latent space, or typically in the first version, particularly in Kingma, you draw there basically a Gaussian random variable. So it's in our RP, P can be for the 100, something like that. Then you feed this into your favorite deep net, can be ConvNet or ResNet or whatever you wish. And then at the output of this, you have an output, and then you have noise, or you feed this output within as a parameter of an exponential distribution, and then you generate the desired object. There are many examples, different associations. This is a basic one. Of course, there are many parameters to fit in this type of model, and because deep latent Gaussian model fit into a problem where the likelihood itself is not explicit, because the likelihood is a marginal likelihood. The thing which is easy to compute is a marginal likelihood, which is you marginalize the likelihood with respect to the latent variable z, so which means that you can formulate the estimation problem as a maximum likelihood problem, but you formulate this problem with a likelihood function which is known, of course, it has an analytic form, but this analytic form is an integral. And remember that even if the latent space is for low dimensional, the number of variables to integrate is of order of hundreds. So which means that the marginal likelihood is intractable. So which is a problem which is rather classical in computational statistics. We call that intractable priors, for example, in Bayesian estimation. And also another problem which is of interest for us, and we change a bit the type of techniques that we can use, is that the number of parameters D, which are, for example, the weights in the deep net, is very large. It can be of order of millions or even more. And of course, because you have many parameters to fit, then the number of observations is also very large. So what is a classical approach to do this? Because this problem is not new. As I said, in computational statistics, the problem is not new. And what was a classical approach in computational statistics was to do something like, which can be, looks like a bit like a gradient descent, but a gradient descent with a special flavor in the sense that you cannot really compute the gradient of the criterion, which here is the likelihood, so the negated likelihood, because if you do descent, you pay to minus. And but of course, there is a very famous formula. Sometimes it's called a Fisher formula, in which you can prove, and it's very easy. It's a three-line computation, that the gradient of the incomplete likelihood or the marginal likelihood can be obtained as the expectation of the gradient of the complete data likelihood, which is integrated with respect to the posterior distribution of the latent variable given the observation. Okay, so this has been the working horse of many models, and where what you typically do in this type of stuff is that you approximate, you compute the parameter by doing something like gradient descent, and you approximate the gradient by running in parallel a Markov chain Monte Carlo method to approximate, to draw samples according to this posterior distribution. Okay, this was more or less the state of the art at the beginning. 10 years ago, I did a lot in this area using either gradient descent or EM-type algorithm. So in EM-type algorithm, this is called, for example, stochastic approximation EM or something like that. So there are many algorithms of that sort. So what is the preferred form in variational in machine learning today? So of course, because of the dimension of the latent space and the fact that you have a super large number of observations, which means that you have to approximate not a single, you don't have to approximate a single posterior distribution, but you have to approximate many posterior distributions. But one type of method which has been used is to use variational approximation. So what is a variational approximation is that you postulate a form for the family of distribution, which depends upon other parameters which are denoted by phi. And of course, you cannot really compute the likelihood function. So, but you can compute easily a lower bound, so which is called an evidence lower bound, elbow. And this lower bound, in fact, is a lower bound of the objective, which is the likelihood, and this lower bound is obtained like this. So you compute simply the Kullback-Leibler divergence between the joint distribution of the observation and the latent and Q phi. So remember that this quantity, the joint distribution of P theta y z, in fact, is not working on the same space. So what you have to subtract the P theta of y, which is the marginal likelihood, and then you have the term which is a KL. This is why, in fact, the elbow is the lower bound. So of course you can obtain elbows, and so I worked also on this topic if you get interested, in order to the way you can produce better elbows. So I will, if I have time, I will explain how you can try to obtain better elbows than the simple ones. So if you look at this, when you do that, what is variational inference for DGM? So you start with a family of variational family of distribution, which is called sometimes the encoder. So the encoder is called amortized, so in the sense that it depends upon the observation through, in fact, also another neural net, so which encodes really. So you start from the observation wise, and you feed this observation into a neural net. This neural net produces parameters for latent variables. So for example, it can be a Gaussian with some mean and some variance, but this mean and this variance depends upon the input. So this is called the encoder. and then you just learn jointly the decoder, so the parameter of the decoder, theta, and the parameter of the encoder by minimizing the elbow, maximizing the elbow. Another method is to use generative adversarial network. In such case, of course, what you do, so you use basically the same generator, but you train them in a completely different way. So it's not about it's basically the same structure to generate observation, but the way it is trained is different, is completely different, because in GANs you use zero-sum games, so it's so you use a discriminator, and once you have the discriminator, what you know is that the optimal discriminator is given by this formula. So it's basically the base formula. So, and then you can say, okay, so if I have the distribution p theta of y, which is the distribution of generator, and if I know also the discriminator, and then if I assume that everything has well converged, so which means that the discriminator is really given by the Bayes rule, so then I have a better estimate of the true distribution in this form, okay, where d theta is a logit of the discriminator. So which means that there is a family of methods called MCMC GAN, where once you have more or less obtained a GAN, then you can try to sample this GAN with, most likely, if everything goes well, should have better, it's a better approximation of P. Okay, so if in all of this setting, of course, what you have is that you have a distribution pi of dx. This distribution is depends upon a prior, and then you have a likelihood term, so and a normalizing term which is z. So in the Bayesian setting, the prior distribution, rho is a prior distribution, L is a likelihood. In generative adversarial network, rho is a generator distribution, and L is derived. It's a logit of the discriminator. In variational autoencoder, it's a bit more subtle in the sense that you have a y which comes into play, so which means that in this time you have the times the prior, is denoted with the PDF there, times the likelihood becomes a joint distribution of x and y, so that's the joint likelihood, and z, which is normalizing constant, is a marginal likelihood. And so what you need to do when you do to formulate an elbow is to be able to obtain lower bound for log of z. Okay, so what are the objectives then? Is to construct an unbiased estimator of the normalizing constant z, which is equal to Lx rho dx, and to sample from pi. Okay, the classical technique to do this is to use MCMC, but MCMC have their problems, and so I basically use a different method, and this is the purpose of my talk today. So my method is based on important sampling IDs. So important sampling IDs, one of the most simple IDs is important sampling to compute this type of quantity. So when you do important sampling, what you do is that you take a distribution rho, say for example rho, you sample ID from rho, and then you estimate the normalizing constant by averaging the estimate of xi, and you reweight by the inverse of the number of samples. So it's clear that such estimator z is an unbiased one. And what you can do typically to improve, if you wish, this estimator is to use a mapping. And so imagine that the mapping becomes invariant with respect to that the distribution rho is invariant with respect to this mapping. So which means that the push forward of rho by t is equal to rho. Then what you can do is that you simply, so you sample from rho, then you compute trajectory according to t. So you compute the orbit of the mapping, and then you obtain an estimate by averaging not on xi, but you average with weights. Of course, you average with weights the orbits of the xi according to the mapping. And what you can expect is that you obtain a smaller variance estimate than the crude IS estimator, provided that the mapping is well chosen. Okay. So of course, what we will do today is that in fact, so of course, if you assume that t should be invariant for rho, so this is a bit annoying. So what I prefer to have is a more general class of estimator. So I can show. So it's very easy. So perhaps we don't have time to go through all the proof, but what I can do, I can extend this to any mapping. So typically I will denote rho k, which is a push forward of rho, this time by the transformation tk. So G is Jacobian determinant. And then you use, and what you do is that you define what is like a generalized proposal distribution, which is a combination. It's a mixture, of course, of this push forward of rho by the mapping tk. and you use a key identity, which is identity behind the important sampling estimates, where you see that fx rho x is equal simply to fx rho x divided by rho t multiplied by rho t. And because you have this a very simple expression, you can rewrite this as a kind of integral with respect to rho with weight wk, which can be expressed like this. Okay, so it's a very simple algebra, and then you obtain an estimator where you have to reweight. So there is an expression for weights. You have to reweight. In fact, you draw from rho, you compute the orbit of the point draw from rho according to t, and then you compute weights according to this formula, which is very explicit. Okay, this estimator might also be seen as a kind of specific application of multiple importance sampling. Okay, so what you can do with this, you can do, for example, you obtain an estimator of the normalizing constant. So this time you take for f, you take the likelihood function. This is an important sampling estimator. For z, which is unbiased, so it's completely trivial there. And the choice of t now is, of course, is very important. And so the idea that we had, of course, which seems to be very natural, is to choose t in order to drive sample from rho to the set where the likelihood is large. And also because you have to compute, remember that you have to compute the Jacobian. Of course, this is very important to have transform t for which the Jacobian is easy to compute. So you have many normalizing flows. So there is a huge literature about how to construct such flow with neural nets also, which I will not go in that direction. We have work in this direction. Of course, there are many very nice work on flows, and which has really changed the way people look at importance sampling. Importance sampling today combined with flow can be very efficient because you can produce with simple distribution and complex flow, you can really build very flexible distribution. But what I use today is, in fact, something which is more classical, which is a conformal Hamiltonian transform. What is a conformal Hamiltonian transform? So it's an Hamiltonian method in which what you do is that you define a potential energy, so which is LQ rho Q. Okay, so you take the log because it's an energy function. You define a kinetic energy, which is simply with P, which is a mass. So now X it becomes Q, and P is a kind of additional variable, and you define what is called the Hamiltonian, which is a sum of the potential energy and the kinetic energy. And you define a conformal Hamiltonian system in which what you do is that you have an Hamiltonian ODE, so a Hamiltonian ODE, which is like an Hamiltonian ODE, but it's conformal in the sense that you have a friction term. What you can prove, which is very easy, in fact, is that for any solution of this conformal Hamiltonian ODE, in fact, converges in the sense that the system is dissipative because you have a dissipative term here. You have a friction term, so it's dissipative. It dissipates exactly a quantity which is gamma times the kinetic energy. So which means that the ionic stationary points of this distribution are fixed points, which are Q star and P star, where the particle goes, the momentum of the particle goes to zero, and in fact Q star it's a local minima of the energy. Okay, you can do Euler discretization for that. So this is conformal vector field. Okay, you can do conformal vector field with this. So it's like it depends upon the choice of gamma. So if you have gamma equals 0, no friction, you have Hamiltonian trajectory, and if you use gamma which increase gamma like this, you obtain trajectory which converge to points. Okay, so message, in fact, it works very well in the sense that if you have here, I have many more works on that, but even in the simple case, so well, it's really this it's called infinite, and it works much better than importance sampling and unimportant sampling, which are considered, unimportant sampling is really considered as a state of the art for likelihood estimation, and infinite works really much better on many. It also works well in the multimodal case, and this is basically you have a very strong exploration property of this model because you sample point and then you optimize. So it's a very good strategy for doing this. The good news also, but I have only 1 minute, so I will conclude there. So the good news is that you can combine this to perform sampling, and you have also the good news. I have many things to do, so it's more like 1 hour would not be enough, I think. The other good news is that we can also define variational autoencoders with this method, and to do variational autoencoders with this method, in fact, is that we might define a new elbow with this estimator, unbiased estimator of the normalizing constant. So we obtain a new elbow, which may be defined as it's an elbow. So it's again an extended elbow. So it's something like that. So I would just conclude with examples where we get examples from this elbow, which shows that we are doing very well. So if you look at these numbers, we are doing very well compared with class state-of-the-art, which is IWEIE, so which is one of the state-of-the-art for this type of model. So in fact, it's a model which is very simple, which is a DLGM model. Okay, so I have many more to say, but I think it's enough for today. Thanks a lot. Question?
Thank you. Thank you, Eric. In the interest of time, unfortunately, I think we don't have time for questions right now.
Too bad.
Thank you very much for this interesting talk. And we'll move on to our next speaker, which is Laura Leal-Taché from Munich. And she'll be talking on deep metric learning.
Okay, thank you, Nico, for the introduction. So indeed, today I want to present our latest work on deep metric learning together with Jenny and Ismail. And so let me start by briefly introducing what is deep metric learning. So in this task, we want to learn a distance function among objects. So for example, if we would have these two pictures with objects A and B, the network unfortunately would say, or would be trained to say, that these two images indeed don't look similar, and therefore their distance should be large. And especially compared with these two images, which belong to the same person, it should say that there's a high similarity and therefore a small distance. Now, while the training is a bit complex, and indeed we will go today through how to train this efficiently, the testing is actually very simple and very powerful. So with a simple thresholding, for example, computing the distance between these two images and just saying, if this distance is above a threshold, we can determine that this is not the same person, while if the distance is below a threshold, we can determine that this is the same person. So with this distance function, we can also cluster different objects and obtain such a representation in which you see here different clusters, in this case of species of birds. So you can see that, for example, these birds with the red head are all clustered together, while if we observe another cluster, we see all these birds which are sort of brownish. And apparently this is the same species of birds. I cannot really tell one from the other. But it actually works really, really well, even for tiny differences. Now, the tricky thing about deep metric learning is actually how to train the network for such a task. So usually we train it with a contrastive or triplet loss. In the simplest contrastive loss, we use one comparison. So we either compare two images, an anchor and a positive sample, which are supposed to depict the same object. And our goal is to bring the distance between these two objects closer together. While at the same time, if we see an image of this spike with compared with another sample, which should be a negative sample, so in this case, another type of bike, the distance between these two images should be pulled further and further apart. And this is how we create our loss function. Now, a stronger loss function is the triplet loss, which uses relationships. So one between the anchor and the positive, and the other between the anchor and a negative image. And in this case, the only thing that we need to preserve in our loss function is that the distance between anchor and positive is smaller than the distance between anchor and negative. So we don't care about the absolute value of this distance. And this actually allows us to train this distance function. So to pull the similar objects together and different objects apart. Now, the thing is that in order to train these models, we need to choose these pairs or triplets. And it turns out that in the huge data sets that we're usually dealing with, there are indeed a lot of pairs and a lot of triplets. but most of them are really uninformative. So for example, this pair or this triplet, where we're comparing a bike with a chair, it's very, very easy for the network to say that the chair is indeed not the same as the bike. And therefore, it's very possible that within a couple of iterations, the network is already learning nothing from this triplet. So usually what researchers have done is spend quite a lot of time in developing special sampling techniques in order to obtain really informative triplets to really define these decision boundaries in a finer and finer way. Now, what we would like to do ideally is to take at least a batch of images and use all the relations in this batch. So not B-half relations, which is what you do with the contrastive loss, or 2B3 relations, which is what you do with the triplet loss, but really all the possible comparisons of samples that you have within the batch. So the question that we aim to answer today is, could we actually take the global batch structure into account when training our neural network for deep metric learning? So for this, we have proposed to leverage all intra-batch connections in our recently accepted ICML paper. And so how we start is, like most deep metric learning methods, we start with a feature initialization, which means that we encode every image of our batch with a convolutional neural network. And so now each image is represented by this embedding. And so in the second step, what we propose to do is to create a graph where each sample of our batch is going to be a node. And this node is going to be represented with a feature embedding, which represents this sample. And now what's going to happen in this graph is a series of what we call message passing steps. So this is indeed a message passing network. And what happens in here is that the samples communicate with each other. So they look at each other's embedding, they look at how similar, dissimilar they are, and they update their own embeddings based on the neighborhood. And this is what I'm going to go into detail in a few slides. Now, the cool thing is that once we have extracted the embedding and we have done this communication step in the graph, now we can train our network, both the message passing network as well as the convolutional neural network. We can train it all in an end-to-end fashion with a classification loss. So there is no contrastive loss, there is no triplet loss. We simply train this for the task of classification. And as we will see, since the comparison is already happening in the message passing network, a classification loss is enough to actually learn this distance function. So now the main question is, what is the message passing network doing? So the goal of the message passing network is to refine the initial embeddings, right? So the embeddings coming from the CNN, by taking into account the relations between all samples in the batch. So imagine that I'm this image of this car and I'm represented by this embedding. Now what happens in this step is I look at all the other images, all the other cars in the batch, and I start comparing all of them with myself. And I see which ones are similar, I see which ones are dissimilar, and I update my embedding based on that. So essentially what I'm doing is I'm taking into account all the other images so that I can make a proper classification. I can have a proper classification output at the end of the day when I train with a cross entropy loss. So let me go a little bit into more detail on how these message passing networks work. So essentially we need to start with a graph initialization. We have nodes and edges, and we have optionally feature embeddings for the nodes and the edges. In our case, only for the nodes. But the interesting part, the learning part, happens here in the middle, where there's this information propagation step across the graph and across several iterations. So an iteration is when a node gathers information from the neighboring nodes and updates its own embedding. And this happens for several steps, which we can consider as several hidden layers. And in the end, what we're going to have is the same graph, the same connectivity, but with nodes that have updated features, right? So now the feature embeddings somehow contain this context, this information from the neighbors. And the more propagation steps you do, the more information you get from further and further away neighbors. So in particular, how we do this in our work is we take, in order to update a node embedding, let's say of node I, we take all the embeddings of the neighboring nodes, and we're going to aggregate them. So note that in here we have a summation, and it has, so this operation has to be an operation that works for any number of nodes, because of course you don't know the connectivity a priori. And this aggregation is going to happen with these learned weights, right? These are the weights that you actually train when you perform backpropagation. Now, furthermore, we have attention scores in order to give different importance to different neighbors. And it's important to note that the weight is actually the same for all nodes, right? So the weight only depends on the number of layers, hence this index L, while the attention depends on the pair of nodes, right? Depends on the similarity between this pair of nodes. And this formulation is actually also the very similar formulation from transformers. And in fact, in practice, we use transformer layers for our task. So here we can see a bit visually what is happening with all these message passing steps, right? So we have image A and B, which are actually depicting the same bird, and images C and D, which are also depicting the same bird. So ideally, what we would like at the end of the day is that the embeddings from A and B become very similar, and the embeddings from C and D become very similar, and dissimilar between each other. So we have here initial attention scores. The first thing that we do is compute the message passing steps. So in this case, for example, we have the update for the feature vector of image A, right? We aggregate this information from the neighbors. The same happens for all the images, all the way to image D. And we end up with these two updated feature vectors for A, B, C, and D. And so a cool thing that is happening is that the features for the samples of the same class get more and more similar as we perform more message passing steps, while the features for different classes get more and more further apart, which is exactly what we want for deep metric learning. And if we look at the attention scores, in fact, between the first message passing step and the second message passing step, the attention scores between similar images, A and B, are increased, and the same happens for C and D. Cool, so just to recap a little bit how the optimization works. So we're optimizing, first of all, the backbone, CNN, and the message passing network in an end-to-end fashion. And this is important for how we will actually do the inference. And the cool thing here is that we're implicitly taking all the intra-batch relations into account in this optimization because of these message passing steps. So now we don't need to sample pairs, we don't need to sample triplets, we can simply apply cross entropy on the updated node feature vectors, and these intra-batch relations are going to be embedded in the feature vectors directly. But the coolest thing is how we actually do inference, right? So if you think about inference, how I presented it at the beginning, you actually have an image A, you obtain an embedding from a CNN, you have an image B, you obtain another embedding, and then you compute a distance, could be, for example, the L2 distance. This doesn't work when you have the MPN also at test end, right? But since we're actually optimizing the backbone, the CNN and the MPN in an end-to-end fashion, we can use the features from the CNN during inference. So we don't need to create batches, perform the message passing steps or anything during inference, because the information has been encoded in the CNN. And we do have an auxiliary loss on the CNN feature embeddings to make that even stronger. But it's already nice that we can actually have inference the same way that any other deep metric learning method does without adding any complexity. So as far as results go, we are state-of-the-art for public data sets. So it works with a variety of objects. So these are kind of the standard data sets that we use for this task. We do have, of course, some errors, but for example, for this bird, honestly, I would have no idea that this is a different kind of bird. So really, when there is an error, it's because the images are looking very, very similar. So in conclusion, we have proposed a method to train neural networks for deep metric learning. But the cool thing about it is that we now don't need to go into careful triplet selection. We don't need to devise complex sampling schemes. So what we do is we use this message passing network in between the feature embedding and our classification laws. And this already captures the intra-batch relationships. So essentially what we're doing is we're making the embeddings of the CNN stronger for deep metric learning. And we also show that we achieve state-of-the-art results without using the MPN and test time. This is important. We also have actually a method to use the MPN at test time, and we explain how we create the batch. So if you're interested, please go ahead and check our paper. So with this, I would like to thank the authors, Jenny and Ismail, and if you have any questions, I will be happy to answer them.
Thank you, Laura, for this great talk. We would have time for 1 or 2 questions. Do we have any from the panel?
Yeah, I have a question. This is, I think, an approach that needs some supervision, some ground truth. Do you see ways to make this more, say, self-supervised in some form?
So we are working on a self-supervised version of this, but indeed this is trained with the ground truth classes, right? So you do need to know that these birds belong to this class or this star belongs to this other class. But one idea could be to take only loose relationships, for example, into account. You could also train it, for example, with attributes instead of the ground truth class, or you could go more the semi-supervised learning way. So train it with by taking an image, performing a series of augmentations, and then saying, okay, this image now needs to belong essentially to the same class. So there could be multiple things that one could do, yes.
All right, great. Maybe one last question from YouTube. And the question is how the neighbors are defined in the message passing network, and if each image has the entire data set as a neighborhood, and does this scale to very large data sets then?
So the neighbors are the samples in the batch, right? So that's why we say this is intra-batch connections. Mm-hmm. So the graph is created with all the samples within one batch. So like one image is not compared to all the elements in the data set, but rather to add the elements in the batch, and then you can change the batch and then make other comparisons.
Okay, excellent. Maybe if there's more questions on YouTube, you can also, or also Eric could check YouTube later and answer questions there. In the meantime, we'll move on. Thank you again, Laura, for this great talk. And our next speaker will be Volker Markel from Berlin, and he'll talk to us on data management and machine learning. Volker, please take it away.
So, hello, can you hear me now?
Yes,
Okay, sorry, there was some problem here. Well, thanks a lot for having me. So I am probably a bit of a outlier here in the sense that I'm a data management and big data systems researcher who is working very closely together with Klaus-Robert Müller in our research center Bifold at the intersection of data management and machine learning. And so I'll probably offer you a little bit of a different perspective today. And that is, I'll talk about the data science process and how to optimize that, and looking at that from the perspective of data management research, where the goal is to scale processes in deployment with respect to human and technical latency. And in order to do so, we tend to draw on methods from computer architecture, statistics, machine learning, distributed systems, compilers, programming languages, and others. And let me make this a bit more concrete now. So I'm sure you all know about those data science processes that consist usually of 5 steps when you build a model, right? That is starting with information extraction that we integrate when we have the data sources. And then one analyzes the data, builds a model, and in the end deploys it. And it's important to point out that a key part of that work when building machine learning applications is information extraction integration. Often that amounts to 80% or more of the effort. And it's also important to point out that this is usually an iterative process until the model is deployed. And if we look at this now, what happens when we deploy such a model? So what happens is first one specifies the model building, the analysis, in particular in a streaming setting, we may want to do so in a way that models may incrementally be even refined. And then the specification is compiled to be executed in a computing infrastructure, potentially on large data sets that are massive, sometimes heterogeneous, need to be integrated. And then one does something with the results, right? So for instance, feeding an application or whatever. So in this process now introduces 2 important latencies. The one is a human latency that happens during specification time. So it's not always easy to specify those data analysis programs, because one has to worry about, if you want to execute this in a scalable way, on how to parallelize that, how to exploit modern hardware and so on. So how to program that is non-trivial. And second, there's also a technical latency, because depending on the system and the architecture, there's also questions of how you can efficiently produce those results with the right parallel algorithm using methods like caching or others. And in order to overcome that, in the data management community, we are looking at, on the one hand, for reducing the human latency into concepts like declarative languages, where one specifies what one wants to compute and not how to compute it. And then there is a component which is called an optimizer that automatically parallelizes, automatically distributes, and automatically selects the right processing algorithms depending on the underlying computer architecture. And then, of course, one leverages pre-processing techniques like indexing in order to efficiently process the data, or hashing. And with respect to the data processing, one looks into parallelization, distribution, caching, and also, as I mentioned, specific algorithms. So let me make this complete in a specific system that we have been building in Berlin that's called Apache Flink. And that illustrates both the data programmability aspect, which is reducing the human latency, and the scalable data stream processing that we use with the technical latency. So first, a programmer would specify a declarative data analysis program. This is, in this case, some graph analytics. And the system itself internally has an algebraic model that it uses that is based on the concept of relational algebra. And the key feature in the context of machine learning is now to combine this with linear algebra and use properties of associativity, commutativity, or distributivity among operations in conjunction with a cost model in order to trade off different implementations and different execution orders of operations. And in this way, the system can automatically arrive at a data flow graph, which describes how the data is being processed, and also how the data communication takes place, if we're talking about compute clusters, or if we're talking about different levels of memory in a memory hierarchy. So how to do all of that in an automatic way that does not require, for instance, an expert GPU programmer or an expert distributed systems programmer. It's also interesting to point out that some research aspects that are currently going on there is to use machine learning to build those optimization processes as well, for instance, by learning cost models automatically and having models based on neural networks or other, entropy maximization approaches and so on. But this all is happening at specification time. It's essentially improving the human latency of this data science process. And now if we look at the runtime, then it is about having efficient algorithms that ensure fault tolerance when parts of the system fail, to do resource management, to have both out-of-core and in-core algorithm, which means when the data fits into memory, you want to process data with special algorithms that take advantage of the specific memory and CPU types that you have. But if the data size, because it might be big data, doesn't fit into memory that you want to process, that external algorithms, for instance, for sorting or data preparation, are used at the same time as the memory management, stream processing, and so on. And we have built this system called Apache Flink, which is an open source system. I'll get to that a little bit more later as well, that addresses those issues and in this way facilitates data-oriented programming for massive data streams. And the impact of this automatic optimization is drastic. So if we have such a declarative program, this optimizer decides on the execution order, on the parallelization strategy, on whether to use in or out of core algorithms, the physical implementation, and also materialization strategies. And in this way, you could run the same program on a test data set on a laptop, which results in a completely different data flow graph than executing it on a big cluster, but it's still the same program. You don't have to change a single line of code. And same thing you could do is run it much later, and after data and the environment has changed, and then you would still have a very different execution graph because maybe you have a different compute cluster, but you don't have to change the program. And this is what really is about reducing those types of latencies. And with that, which was a bit more general overview, I want to talk briefly about one specific research contribution and highlight, or before I do that though, just point out this is an example of such an optimization for natural language processing pipeline that consists of a variety of operators, and optimization would include, because of algebraic properties of those operations, to change the orders between those green boxes that are operations, and also, for instance, change what's gray here, which is the different communication patterns in the compute cluster, that is local memory or network broadcast, also between those operations. And of course, nobody really wants to hand tune that. That's why it's important to have those automatic operations. And there's lots of different aspects that can be considered in improving latency and throughput in those systems. And we have made several contributions here in compression and also in parallel programming and latency reduction that have earned us a couple of awards. But I want to focus on one specific highlight that we just published at the International Conference on Data Engineering this year, where we also won the Best Paper Award for that. And that's about contraflow approaches in data flow systems. Because if we talk about processing data, as the data flow systems are good because they scale in clusters and things can be distributed. But of course, when you want to write your programs, in particular also in the context of what you do in machine learning applications, you often want to have iterative algorithms, right? You have loops if you want to build page rank or k-means clustering, a gradient descent, or training your neural network. And the contraflow can become quite complex. It can have nested loops. Also, there could be if statements inside the loops, which all is quite of natural, obviously. But this is all a problem if you want to parallelize and scale out the architecture. And in a data flow, it's hard to do that. And what we have come up with is a method for compiling those imperatively written contraflow jobs that you might know when you write in Python or when you write your TensorFlow programs into a single data flows job that then can be scaled out and compiled and executed in a large compute cluster. And so the way to do that is, I'll show that, but just to give you an example, is here we see two separate systems. So one that provides specific support for loops, and that's the system Flink that we talked about, which is quite fast, but it's complicated to use because you have to do second-order functional programming in order to do so. And there's other systems, some of you may know Spark or SystemML, that would actually run loops, or in this way, contraflow in separate jobs. And in this way, it reduces a lot of overhead, and the execution time of a job would be much, much longer. So just to make it a bit more concrete, so systems like, for instance, Spark or SystemML, that's some common Apache projects, what they do is they run a data flow in separate jobs where you have a driver program that launches a data flow job on the cluster for every invocation, for every time a loop is being executed, each time the step function is executed. And what this means is really there's a lot of overhead because one has one constrains internal state to one step, and one also has a synchronization barrier among those different potentially parallel computations. And instead, if one runs the data flow job on the cluster directly in an iterative way, one needs a data flow that may have a cycle. So it's a cyclic data flow, and that's what those other systems cannot support. And then one does not have to worry about the state. One can keep the state between the steps, and one can also pipeline the execution. So this offers a good amount of benefit. And the trick in order to do that is, I will not go into too much details for that because that's probably a bit off topic for a machine learning audience, but one uses some trick from compiler technology, which is called single state assignment, which essentially means one takes control flow statements like while loops, do while loop, break statements, continue or if statements, and puts them in the single state assignment, which really means one creates new variables and makes out of any of those control flow statements a function invocation that then can be mapped into a data flow. So this is an example. And the only thing to point out here is there's an original program that has some if statement and a loop on the left side. This is translated into an intermediate representation. And the key thing is you see this variable pref is in this case translated into three different variables, pref1, pref2, and pref3. And there are so-called special functions that you see here, for instance, for pref2 that determine a conditional, like the if statement, and this is what the pref3 does here. And what this really means, one translates this into a data flow where each data flow consists of a data flow block that is without any imperative constructs. And the only thing is at the end of such a block, one may have a jump, and this jump may be conditional and it may be cyclic. And if you do so, then you can actually achieve this optimization to execute a data flow that is coming from a imperative program. And so just to summarize that, so in this way one can use the simple imperative programming that many of you know, of course, all of you know, I'm sure from your standard programming languages, but then compile it into data flow jobs that can be executed on massive clusters, and one can do optimizations, and I cannot go into the details here, but essentially one can, if there's some data that's invariant in the loop, like a large data set that's used computed only once, one can leverage that across the loops, and one can also have pipeline execution, and one achieves up to 2 orders of magnitude speed ups over the existing system. So there's a drastic impact. So this is just to give you an idea on this highlight. And then I'll switch back to, I said, the system that I mentioned before that we built called Apache Flink, because this is probably the biggest success story that came out of Berlin and our competence center. And that is a data flow system that by now has a community of meetups that's almost 30,000 people. About 870 open source contributors to date, so not people who use it, but really people who advance the system worldwide. Yeah, almost 50 meetup groups, and also, yeah, probably more than 50 companies by now that use it, and there's also some entrepreneurship that has been going on in that space. And there's highly engaged users of that system. For instance, Alibaba in China is running that on a 1,000 node cluster with 5,000 cores and processes millions of events per second. King runs rather complex jobs. That's an online game company in Sweden that runs 30 billions of events daily with that. And a telco in France, we have a telco that many of our French partners in the workshop probably will know, runs also Flink applications with 10 billion events, which are 2 terabytes of state processed daily. And there's lots of users, so you can see just a list of the companies. So lots of big American companies from Silicon Valley, like Uber, or also Netflix, but also in China, like Tencent or Alibaba, and a large community around it. So with that, I will conclude. So since this is a bit off topic for some of you, but maybe still an interesting impetus or impulse. So there is lots of current and future research issues that also border this, intersection between machine learning and data management, and this on the systems architecture space, where It's about, you know, exploiting modern hardware, but really about then learning data management components in this context of what people would call System 2.0, like learning indexes, learning cost models or optimizers. There's lots of intersection also with respect to data programmability, like combining relational and linear algebra, Ida has mentioned, or also cross-platform optimization. If I have different systems from which I draw the data, how do I integrate that efficiently? At the same time, if we move into the Internet of Things, those types of environments, it's about processing on the edge, heterogeneous distributed environments. So we are actually currently building a new open source system that is succeeding the Flink system that I mentioned, which is called Nebula Stream. I've given you the URL here, that can handle millions of distributed sources and queries and deals with continuous operation under evolution. And at the same time, of course, it's important to look into infrastructures for sharing data algorithms and resources like compute and storage resources with respect to secure execution, and of course also specifying and enforcing compliance to organizational and legal constraints like privacy. So with that, thank you very much for your attention.
Thanks, Volker. This was very impressive, in particular also the results and the speedups you can get. We have time for a few questions. Maybe I can start with one. So you already mentioned that you borrow a little bit from compiler technology. And then I was wondering, do these ideas that you presented for a data analysis problem, this data flow networks, would these also translate to general purpose optimizations in compilers? So when I, for example, implement my my computer vision algorithm and want it to run as fast as possible on my CPU on a single machine, would these ideas also work there or not?
So I would argue that, so absolutely they would. So that's the first statement. I would argue that many compilers for a single machine, however, would take those optimizations already into consideration, because there it's, if you wish, the problem space is, I would say, a little bit easier, because you're focusing on the memory hierarchy in your machine, you're trying to do latency hiding and so on. So in this respect, compilers already do have concepts like, for instance, exploiting sparse computational dependencies, and like even, you know, the old Fortran compilers already exploited some of that, and modern C compilers do those as well. So in this way, the answer is yes. So if you really targeting that, let's say, for instance, across several graphics cards, and you want to parallelize and distribute computation, then you could benefit from that. So if it's already, you know, on your single CPU setup, then actually I would venture to say that if you use the right compiler, you probably would have that technology.
Mm-hmm. Yeah, maybe the compiler could benefit from some machine learning as well.
Yeah,
thanks.
Absolutely, they can, and that's the interesting intersection here. You know, learning, you know, some of those performance models, right? Because this is essentially what we're doing in data management, so that you know, for those operations, depending on the physical computer architecture, what kind of performance model do you have, so that you can string together your code.
Yeah, thank you. Do we have maybe one more question before we have to conclude? Otherwise, maybe you can also visit YouTube and check for people's questions later. Then we would conclude this session. Thanks for all the speakers again, and thanks for all the viewers. We'll be back in about 20 minutes with the next session. Thank you.
Hi, everyone. Welcome back to the French-German Machine Learning Symposium. It's my great pleasure to introduce our next speaker, Bernhard Schölkopf from Tübingen, who will talk about causal learning. Bernhard, the floor is yours.
Thank you very much, Daniel. It's an honor to speak in this workshop. And I would like to use the next 15 to 20 minutes to tell you a little bit about causal learning, more on a conceptual level, without going into details, but including a few pointers to projects and papers where there are details. So the whole story for me started around 10 years ago. So we had started working on causality maybe 15 years ago, initially focusing on the problem of causal discovery. But around 10 years ago, we started getting intrigued by how to use causality for machine learning. And remember, one particular problem we discussed was this neural net tank urban legend that probably many of you know. So in this story, there's a neural net which is trained to classify tanks with high accuracy. But subsequently, it's found to have succeeded only by focusing on one particular feature. Different versions of the story have different features, but let's say it's the weather. On focusing on this feature that contains information about the type of tank due to the data collection process. So let's say all American tanks were collected on a sunny day and all Russian tanks on a cloudy day or something like that. Now, clearly, such a system doesn't exhibit robustness when tested on new tanks whose images are taken under different circumstances. And that's what they found. It didn't work when they wanted to deploy this system. And at the time, so my hope was that somehow, or feeling was that somehow a classifier that incorporates causality could be made invariant with respect to this kind of changes, or could be made robust. And I had been interested in invariance for quite a while, working on it in the context of support vector machines and kernel PCA. And I would like to take this opportunity. So one particular person that I worked with at that time was Olivier Chapelle, working on invariant kernels. And Olivier Chapelle, as many of you know, passed away last year, almost to the day today. So 1 year and 1 day ago. So I would remember him and dedicate this talk to Olivier. So our first project in this direction, so we had been thinking about this problem for several years, and then I got an invitation to give a keynote talk at NeurIPS, and I was very eager to speak about causality and to speak about this problem, but we hadn't really, the thing hadn't crystallized yet, so we forced ourselves, went to the Black Forest for a week, and with Dominique forced ourselves to start putting something to paper, and this resulted in this first paper, which was later published under a different name at ICML, which was about robustness, about invariance, and somewhere in the introduction it also says it's about how to leave the comfort zone of IID data. So that's where it started for us. I should say. There's a completely separate thrust, and in the end, I think they kind of converged to something similar. And that thrust was started by Joshua and others, and that was about disentanglement and how to find the factors of variation underlying data. And I remember at the time I was in the advisory board of the CFAR program, and Joshua was talking about this problem for the next grant extension, and to me, it sounded like he's speaking about a causal problem. So I kept telling him, look, I think this is really about causality. And I think by now we have kind of, maybe he has moved a little bit in the causal direction, and I moved in the deep learning direction. And I think there's now a lively field at the intersection of those two. And I want to tell you a little bit about this today. So I would like to argue that disentanglement, as it's studied now in deep learning, has something to do with independence. That's what people usually connect it to, but this should go beyond statistical independence and go closer to causality. And one example, this is also a computer vision heavy workshop. You all know this object called a Bechet chair. And when you see this object, of course, your brain makes or when we see any object, our brain makes the assumption that the object and the mechanism of perception, so in particular, the direction from which we look at it, are independent. And our perception builds on this assumption, because if we violate this by looking through this particular hole, thus coupling the perception process, the direction of gaze, or the direction of viewing and the object structure, then perception fails because we perceive a structure which is in reality is not there. So this is connected to this generic viewpoint assumption. It's also connected to something called structure from motion. Because if you think about, if you move your head, if you take an object, you move your head around it, then you implicitly assume that as you move your head, only the mechanism of perception changes, but the object itself is invariance. So we postulate that the causal generative process is composed of autonomous modules that do not inform or influence each other. And so we've been trying to use this principle in different guises in deep learning. And this is very much an ongoing process. And so before showing you some examples, I want to first tell you a little bit more about how to formalize this principle, or what it means, slightly more formal than so far. And so the examples will be in these directions, but first let's formalize it a little bit. And to this end, let's first remind ourselves what is a structural causal model. So this is one way to write down a causal model. Maybe you are more familiar with causal graphical models or graphical models. So a causal graphical model would be a graphical model where the direction of the edges, so a directed graphical model where the direction of the edges corresponds to the direction of causation. But underlying each such causal graphical model, there is a structural causal model, or there's actually many structural causal models giving rise to the same one. So the structural causal model actually contains more information. And so we start with a DAG with a set of vertices. We think of the vertices as observables, the arrows as direct causation. And we assume that each vertex is each random variable or observable. Each vertex is a function, a deterministic function of its parents and a noise variable. And these noise variables are jointly independent. And the noise variables are also called unexplained. So sometimes the shorthand U is used. And this is a structural causal model or a nonlinear structural equation model. And it has various properties, Markov properties, etc. And people have spent a lot of time trying to infer such models from observational data. So if you can make interventions, then it's sort of relatively easy to learn such models. But if you're only observing, so clearly, if you specify distribution over the noises, this implies a distribution over the observed variables. So given that distribution, given even complete knowledge of that distribution, turns out it's non-trivial to reconstruct or to infer this model. And that's the problem of causal discovery. So that's what usually is being studied. But today I want to talk about a slightly different problem. And one could say that's the problem of causal representation learning. Because these structural causal models, one could say, are in a way already at the symbolic level. Someone gives you the symbols, and now you're asking the question how they're related to each other and what kind of processes can you do with them. So it's a little bit like the pre-machine learning version of AI. But in reality, we might not be given these causal variables. So we might want to infer them from high-dimensional data. And so we have to have high-dimensional inputs and then somehow a mapping to this symbolic level. And then in that level, somehow embed a structural causal model. So, so what do we, I promised I'll say something about disentanglement. So first of all, I should say, given such a model, then I can always write the joint distribution in a particularly nice factorization, which is this one. So it turns out, essentially, since the noise terms are independent from each other, I can write the joint distribution as a product of conditionals, where the conditionals are only conditioned on the parents of the respective node. So that's a much lower dimensional object than it's just a generic decomposition of the joint distribution. So that's nice. But we will ask for one more thing to hold true, and that's related to this assumption that I told you about before with the Béchet chair. We will require that these objects here, these conditionals, are also independent from each other in the sense that if I change one of them, for instance, by an intervention or by a suitable domain shift, if I change one of them, it doesn't automatically change the other ones. So I can intervene on them independently, or if I change one of them, the others remain invariant. So that's a particular kind of assumption, which is not the same as statistical independence between the xi. In fact, the xi, if the graph is non-trivial, will not be statistically independent from each other. So let's assume both these things are true, then we could call this the disentangled or causal factorization. And there's a special case if the graph is trivial, so there are no parents, all the nodes are disconnected, then this disentanglement will simply reduce to statistical independence. And traditional disentanglement methods look at statistical independence, but I think it's only part of the story. Now, if this is a disentangled factorization, what would be an example of an entangled one? Well, an entangled one would be, for instance, this kind of factorization, which you can get by applying the chain rule of probabilities. And there are many such factorizations, because for any possible ordering or any permutation of these indices, you would get a different such factorization. Now, while these factorizations are mathematically valid, it's important to point out that they don't have this nice disentanglement property, because if you now change, for instance, if you were to change one of these mechanisms, so these things in the causal graph we think of as physical mechanisms, if we change one of these guys, of course, the over distribution changes. Then typically, if we then factorize that distribution according to this equation, typically all of these terms will change simultaneously. So we don't have this kind of sparsity or locality. And that leads to an assumption, which one could call the sparse mechanism shift hypothesis. And this assumption says, so I just told you in the generic case, all of these guys are coupled to each other and change at the same time. Now the assumption is, which is a physical assumption about the world, that for the causal factorization, this is not the case. So for the causal factorization, if one distribution shifts to another one, let's say we have two distributions in the real world that we think are related to each other, then we would assume that this change between the two distributions manifests itself sparsely in this disentangled factorization. So only few of these terms, or at least not all of them, should change simultaneously. And so I'm going to have to speed up a little bit. I've been talking too much about the basics. So there are different ways we've applied these ideas. One is in a project about learning independent mechanisms. So here we have a competitive system that, given distorted versions of images, tries to learn the mechanisms that led to these distortions, and automatically identifies these mechanisms and automatically undoes them in order to sort of classify the distorted images. And then turns out we learn mechanisms that transfer to other problems. In this case, they transfer to a completely different kind of characters without retraining. So that's one example. Here's another example where we try to learn low-dimensional representations of images which have certain properties that make interventions possible, or that make interventions sensible. And in this case, the type of interventions are what one could call hybridization, that you combine certain latent representations from one image with another one. This is a work of Michel Vissel. And here's, for instance, it leads to an intervention which you could argue is intervening selectively on the background of this chicken. Or here's another example where we have two real images on the left and on the right, and then we produce a synthetic image in between, which is not an interpolation, but you could say some kind of causally meaningful interpolation, because this looks a little bit, this is a teddy bear, it's a koala, it looks a little bit like a koala teddy bear. Another example, here we try to put in the causal bias using a suitable structure, where we learn an autoencoder that embedded into itself has a structural causal model in a generic form. So you can translate each structural causal model that's based on a DAG into such a topological ordering. And it turns out that even though in this case we don't explicitly enforce independence disentanglement, we do get good reconstruction quality, good FID scores, and also sensible disentanglements, but I won't go into further detail on that. A more recent, or actually more recent than the first one, we started working with this in 2019. This is a project where we try to do something like this thing here. But we try to do it in recurrent systems for dynamical processes. So this is using a certain type of recurrent network where you have sort of modules that have a default dynamics and that sparsely interact with each other. Most of the time, they just follow their default dynamics, but then sort of mediated by an attentional bottleneck, they sparsely interact with each other. And that gives you another kind of causal or modular decomposition of this overall process. And just to give a few pointers, so some of these works, so this one was just appeared at iClear, and there's a few related projects. There's a follow-up project of this one already, and some other projects here. I also wanted to mention this one. This is on disentangled representation learning from correlated data. So this is trying to evaluate the standard disentanglement methods and what happens to them if your data are actually correlated, which is, of course, often the case. So in a sense, the intuition is if you, like you might often see, I think this example that Joshua once gave, the presence of a fork and a knife on the table is, of course, strongly correlated. But that doesn't mean that they are one object. You can still separately intervene on forks and knives. And if you wanted to sort of reconstruct a table scene, you probably would like to represent fork and knife separately. But if you then train on correlated data, then a standard statistical method is not going to nicely factor out this representation. And so in this study, we compare a lot of methods in that respect, and then also suggest some ideas how to handle that using, for instance, using weak supervision. Another project I want to mention, this is about connections to reinforcement learning. So here it's kind of building on the idea that the search for invariance or the search for sparse changes or sparse responses of environments to your actions is actually a useful bias or a useful reward for reinforcement learning. So that's another paper which will appear at ICML this year. And maybe I will try to come to the end now. So there's a lot of discussion lately, not just on disentanglement, but also on object-centric representations. So from my point of view, and I don't know, it would be interesting how the computer vision people see that. From my point of view, object-centric should be a special case of a real causal generative model of a scene. So object-centric means you want to factor out certain properties of the object, factor it out from other elements of an image, other objects, or lighting, orientation, position, etc. And I'm also quite interested in causal generative scene models. We started working on this last year, and we are currently working on another paper in this direction. So I'm going to skip this. So this is my favorite application of causality in scientific data analysis, where we found exoplanets, and we were very lucky because it turned out later one of the planets that we found ended up being the first one that was in a habitable zone around its star, and was proven to have water vapor. So my conclusion slide. So the long-term goal here is to learn causal models from multiple tasks in multiple environments, and I think they need to reuse components, and that probably requires that components are robust across tasks. And I think a sensible inductive bias for this is to look for independence. Independence in the sense of causal mechanisms. I talked a little about disentanglement. I have to admit I find the problem not yet sufficiently well defined, and we're trying to contribute to that. I think overall we have made a lot of progress in representation learning, but usually that refers to the representation of fixed probability distributions, so to the IID setting. But I think our brains need to represent causal. They should represent causal modules that capture not just one distribution, but a whole class of interventional distributions. and shifted distributions. And I think it's totally open how we represent those. And probably it has to do with also with reinforcement learning, causality, planning, reasoning, etc. And one could say, well, it has to do with thinking in this sense of Konrad Lorenz. And I was tempted. I took a snapshot of Yann's talk yesterday, so I thought I can show a zoom inside a zoom now. I think so. I agree with these challenges. I think I would even argue that the challenge 2 and 3, I think causality has to do with all of them, but I think the challenge 2 and 3 may in the end be very close to each other. Because so I think Yann was citing this book here that he took from Jitendra. I would like to add the book of Konrad Lorenz, where Konrad Lorenz says that thinking is actually nothing but acting in an imagined space. So these models, the models to plan complex action sequences, are in a way the first step towards thinking and reasoning. So I think with that, I would like to thank you for your attention and give you some pointers for further reading. Thank you.
Thank you, Bernhard. Thank you very much for this very interesting presentation. This was quite exciting. There is some questions on YouTube as well. So if you have a chance to look into the YouTube chat, I think that would be best. Also, we can take some questions maybe later in the break, but in the interest of time,
I don't have the chat open. So if you have it handy, maybe you can just read one of them to me. Otherwise, if I start looking for the YouTube now.
Yes. Let's do them in the break because we're a little bit over the time already, and I don't want to cut anyone else's time. So Jean, maybe if I can ask you to share screen. And...
Sure.
So the next speaker is Jean Ponce from Paris.
Do you see my slides?
Yes.
Okay, great. All right, so hello all. So today I'm going to talk about deblurring sharp images. I will come to what it means in a second. This is part of this is the work of Thomas Eboli, a student of mine, and Qian Sun at Xi'an Jiaotong University in China. And he's the co-advisor of Thomas. And this is part of a more general kind of program for my research where I like image restoration because I think it's a good topic for machine learning and for vision, because we typically have a good physical model of what's happening. We have good image formation models. We have pretty good priors and natural images, and we can relatively easily generate pretty good simulated training examples, which is not the case always in vision. And what I like as well is that often you can mix the kind of the classical variational type of approaches, inverse problem approaches with deep learning, CNN type of stuff. So I think it all fits well together. And of course, what I will talk about is related to what Julien Béral talked about earlier. Okay, so the specific problem I'm going to assume is that I'm going to assume that I'm given some raw images, and that I want to deblur them, demosaic them, and I will come back to what demosaicing means in a second, and denoise them as well. So the way we are going to model the process is that you have a camera. It generates in the image plane a sharp continuous image X. This image X is transformed into a blurry continuous image B by the camera optics, and that can be related to motion in the scene or to defocus, but also to the actual PSF of the lens. I mean, a lens doesn't image a point into a point; it images a point into a blob always. And that's what I mean in the title by deblurring sharp images. So you have this perfect image X, it goes to a blurry image B, and then this continuous image is going to be converted into a digital image by your sensor. And as Julien pointed out earlier this morning, most imaging centers use this color pattern with little filters in front of each pixel. So what the camera observes really is a filtered black and white image that then you need to interpolate to recover a full RGB image. So all this here happens in the analog domain. After analog to digital conversion, you will get a mosaic image behind the Bayer pattern. And what you would like here, now we are in the so-called linear RGB realm. What you would like is to recover the a high resolution digital image, small x here. Okay. So you can do in two ways. You can do it by first demosaicing the image, and then once you have done the demosaicing, you can deblur the image, or you can try to directly demosaic and deblur the image, denoising it at the same time. This is a bit different from what people typically do, where typically people assume that the blurring and the deblurring happen in the sRGB image. So the sRGB is what your camera is going to give to you. And that's what usually you are going to store as a JPEG image. But after starting from the linear RGB domain, where all the physics are happening, if you want, in the digital domain, then you have your camera internally does some image processing that's quite nonlinear to create the image that you are going to record and store. Okay, so physically the blurring process is not really happening there. It's happening between the camera and in the linear RGB domain. So we are going to work in the raw domain right after the conversion and in the linear RGB domain. Okay, I cannot cite all the work that has been done in deblurring and denoising and demosaicing all over the years, because there's been a huge amount of it. Let me just focus on a couple of things. We are going to use later some of the work by Bernhard on estimating PSF and removing PSF blur from images. We are going to use the ISP pipeline from Brooks et al. That allows you to take from that models, if you want, the physics of the and the processing of the ISP pipeline. So it allows you to go from an sRGB image raw to a linear RGB image that you can use. So you can generate synthetic examples for training. And then a key component we are going to use is a recent upsampling method by Zhang et al. From ETH. So our model is quite simple. This is the visual forward model. The image that you observe, that is the raw image Y, is obtained from the linear RGB image X by applying to a non-blur, we are going to assume it's not a blur kernel due to the optics of the camera, and then a mosaicing operator that's going to filter the images and then down sample them on the Bayer grid. And then we are going to have some noise, and the noise we are going to assume depends on the colors, the color level, the intensity level, and it's an affine noise with two parameters corresponding shot and read noise. Okay, so this is the model we are going to use. The typical way people have done it before is rather by using a two-layer models, where first you demosaic the image using a demosaicing operator, and then you look at a pure deblurring problem. Okay, so we are going to compare the two approaches, and we'll see that in fact the joint model works better. So the approach we are using is fairly classical. You take we are going to formulate the recovery of the image X as a regularly squared problem, where the regularizer omega gives you a real image constraints. This is often done. We are going to solve by introducing an auxiliary variable z that we are going to force to be equal to x, and so we have this simple model. And what we are going to do is we are going to do iterations. We are going to increase the parameter beta so that z and x are going to become closer and closer. We can use, of course, the same approach in the two-stage model. In this case, again, you will have a separate demosaicing function, and then you will have also this thing with the auxiliary variable z. So in quadratic splitting, what you do is you are going to have an iterative process, and you are going to iteratively solve for the z variable, the auxiliary variable, and then you are going to solve for the x variable, and the two are going to be solved using solved for using different methods, and then you increase the beta parameter at each iteration to force x and z to coincide at the end. You need to initialize the process. You can initialize the process by taking the initial image normally, or in our case, the mosaic method obtained by some method and another. This is a very simple iterative process. You can use more sophisticated methods such as ADMM, but it has turned out to work pretty well in our case. So to estimate x, basically, you have to solve this optimization problem. The optimization problem is the same for both the one-stage and two-stage methods. And basically, the only thing you need for that is to write the proximal operator phi for your regularizer. And in fact, in our case, we'll do just like Julien did this morning. In the end, we'll replace a closed form regularizer by a learn closed form proximal operator, by a learn proximal operator. For the estimation of the auxiliary variable, you simply have a least squares problem, a linear least squares problem, which a priori is easy, but the variables and the operators are huge, so these things can be computationally quite expensive. You have very efficient methods based on fast Fourier transform. You can also use conjugate gradient method or fixed point iterations. The fast Fourier transform method tend to be more efficient. In the one-stage method that we are using, using the FFT method is a bit more complicated, because what we want to do is take into account the fact that the blur is not a gray level blur. Blur depends on the wavelength. In particular, you have lenses are affected by chromatic aberrations due to the fact that different wavelengths are not refracted in the same way. Okay, so you are going to need to use blur kernels that depend on the color, the red, green, or blue color. And then, of course, you have the decimation operator, DR, DG1, DG2, and DB, corresponding to the fact that you go to a full resolution frame to a lower resolution when corresponding to each one of the two components. They are in typical Bayer patterns, you have two of the pixels are green, and so you are going to need to combine those two. And then you are going to solve for Z channel by channel, so for R, G, and B. And this, to do this very efficiently, what we did is adopt the fast Fourier transform and of Zheng et al. To our case. You have to be a little bit careful because of the mosaicing pattern. All right. With this, you can write a function such as this one that will take as input the raw image, the kernel value that you assume to be known, the mosaicing mask, and a bunch of parameters, including the parameters related to the noise. The way this function is written is simple. That's one of the beauties of image restoration. You have interpretable things, you know what to do. So we are going to learn the weights that are used in the half-quadratic splitting algorithm from the noise characteristics. Then we are going to initialize by using some separate demosaicing algorithm. The better the algorithm, of course, the better the initialization. And then we are going to enroll a few iterations of HQS. First, we'll compute Z using the efficient FFT least square solution. Then we will have a learnable proximal operator. This is again the plug and play prior that Julien talked about this morning. So in this function, you have several parameters that are learnable. You have the parameters that for predicting from the noise parameter, the beta and gamma parameters. You might have learnable parameters in the mosaicing function, and then you have learnable parameters in the proximal operator as well. And this function will output a linear RGB image. And of course, you could write the same thing for the two-stage function. The difference is that the demosaicing is done once, and once the demosaicing is done, you never operate on the raw image anymore, and so you never question your demosaicing if you want. So to train this thing, we use synthetic data. Look at my watch, I don't know how much time I have. Synthetic data where we take sharp, good quality sRGB image. We convert them to raw images using the pipeline from Brooks et al., which is a good physical model of what's happening and also is differentiable. Then we submit the image to RGB blurring with different kernels depending on the channel, and we basically create kernels, and then we rotate and deform the kernels a bit depending on the color, and then we add a good affine noise model against from Brooks et al. to noise up, if you want, the image. All this is a training for, but we also need a loss to supervise. We need to supervise the training function. And so what we do two things. We consider both, for ground truth, both linear RGB and sRGB models. The first loss that we use, we take the linear RGB image X that we are given, and then we minimize the difference between what our algorithm, let's call it FRO, computes from the raw image and the kernel and the mosaicing operator. Or we can also take an sRGB ground truth, and then we need to apply the raw to sRGB pipeline S to our function, but S is again differentiable. So for both functions, we can backpropagate the error throughout the functions and then train our model accordingly. So we did some testing on synthetic data. I'm not going to spell out all the lines in that table. The main message is that it works pretty well. So in bold, you have the best method over some standard data set without and with noise. What is interesting is that in the end, so we want to operate on linear RGB and on raw images, but in the end, the images you're going to look at are the sRGB. And so it turns out that when we train with sRGB supervision, of course, we get better results in the sRGB domain, and we can get quite significant improvements in the reconstruction. And the last two lines show that using a good demosaicing method for the initialization actually makes a difference as well. You should always do that. Here are some qualitative and quantitative examples on synthetic images. So our method is on the right, and as you can see in the zoomed in portions, this gives a sharper result than the two-stage method. And again, those are two good demosaicing and deblurring methods. It's a bit more sharper and the details are a bit better. And then we got that from Bernhard and former students. So those are Schuler did for his PhD is estimated the PSF and an image. Again, this is a sharply focused image. You estimate the PSF either for calibration or for an estimation process. So we took that image and we tried our method on this, and here we show a comparison between the original image on the top, what Schuler obtained with the first, I think 26 is wrong, I think it's the first technique here, and what we got. And if you zoom in a bit, you see that we are a little bit sharper. What's interesting is that there are some chromatic aberration that are, of course, present in the original image. You can see the red band here and the green one underneath. They are still, and they seem to be a bit inverted in Schuller's method. It's a bit difficult to see, and they are mostly gone in hours. This is an example from a real image from a photographer. And this is the input image, and this is the deblurred image. The PSF in this case, again, this is a sharp image. The PSF in this case is the same camera setting as in Schuller's setting. So we had the PSF and we could remove it. And we also did some PSF removal comparison synthetic images where I think worked well. One thing that I find interesting is that we are all happy about this. And then we took this image here. And this image is quite saturated in parts. And it's taken with the Canon 5D. It's an expensive camera, but still it saturates. And here in the middle is the results of our method. And you can see, for example, in this bar that has become green. And you have these big stains, these big color stains on the thing. And so we wondered at the beginning what it was for. Then we looked at the data. On the left, you have the raw image signal along the vertical line here. And on the right, you have the sRGB channels. And you can see that the signal in both cases skipped when the image gets saturated. And so, of course, the linear model that we have doesn't work anymore at all. Okay, so there have been a few works attempting to deal with saturation, but it's a complicated problem. So as a first attempt, what we have done is to just train our method with saturated images that we generated, again using a mixture of the let's say that the ASP pipeline and the physical model. So on the left here you have the original blur image. On the right you have restoration using White et al. That estimates the motion directly from this. At the bottom, we estimated the motion using Pan et al. In both images. This is using 2-stage and this is ours. There are still some artifacts. Let me show you a close-up. And again, we don't deal perfectly with saturated images, so this is still open for us. But you can see, for example, here on the left, that the 1-stage method gives much sharper results than the 2-stage methods. So I'm done. So what's next? Next, we want to deal with chromatic aberrations. So what I've shown you is simple chromatic aberrations, but you have many types. You have something called color fringing. You have lateral, but you have forward chromatic aberrations. We want to take those into account. We want to train not just from synthetic images, but from real images. And so we have some ideas about that. We want to bring together what Julien talked about this morning with Bernhard Schölkopf, super resolution, and with Thomas, demosaic and deblurring work, and put them together, also includes PSF prediction. And we want to apply this to amateur and professional astronomy. So I don't know if Bernhard is aware of that, but we are, Julien and I, also starting to work on exoplanet discovery with people from Observatoire de Paris, but in the optical domain. And also Yann LeCun has bought this very expensive telescope, and we want to super resolve and deblur and denoise these images. So astronomy, I think, is a great field for that. Thank you very much. I'll be happy to answer any questions you may have.
Thank you, Jean. Thank you for your presentation. We're a little bit short of time again. Is there maybe one short question? I'll have one very short question. Your method, Jean, assumes that you know the mosaicing pattern. Sure. Is there ways to somehow infer that from data as well, so that I can just apply it to a random camera without knowing what mosaicing pattern it is?
Normally, if I took a random camera, I would open the manual and look for the mosaicing pattern.
That's that was short question, short answer. Thank you.
But you can imagine maybe some application. So we haven't thought of it, but yeah.
Okay. Thank you very much, Jean. Let's take the further discussion into the break as well. Now we have our last speaker of the symposium, Christian Kersting. Could you share your slides? And wonderful. Yes, Christian, the floor is yours.
Yeah, thank you. Thank you for the invitation. It's an amazing workshop. I made too many notes, but that's a good sign. Yeah, so I would love to talk a bit about neurosymbolic concept learning, and all the credits go to Wolfgang, Patrick, Carl, Adam, and Hikaru. So what is this all about? I think in particular in the last 2 years maybe, and we have heard a lot discussions again about, well, do we need symbols? Where do symbols come from? Do we really need them? Is differential programming anything that we really need? I don't want to give you an answer here. I take a very pragmatic view. I think we should just embrace both of them and really use them. And let me illustrate that by slides from Mauro from MIT. And it's all about visual reasoning, but keep in mind, I'm actually quite new to computer vision, but we have a scene here. And now you would like to not only understand that they are objects, but you would like to also infer somehow features of the objects, right? And we can do that. You take any of your favorite deep neural network for that, and you can do something like that. Why? Why is that interesting? Well, for example, for visual question answering. And I think what you see here, you can do that instantly as a human, and somehow the game is now to also get machines being able to do that, right? So for example, you can ask now, what is the shape of the red object? But now, because we have a symbolic representation, it's a very simple task, right? It's just in a sense like what Volker Markel was also talking about. It's a kind of data management question and inference question, right? So you just check out which object is red, and then you can also talk about the other property of that object and say, well, it's a sphere, right? And you get the answer. And so there are a lot of interesting models now popping up on that. Here you see one from MIT that is actually blurring, in my opinion, a bit the distinction between what is symbolic and what is, so to say, deep or neural or differentiable. But it's less about the system in particular here, because there are tons of other approaches already existing. Also, if you take a slightly different perspective, for example, from the probabilistic perspective, how to really get programmatic abstractions and trying to make use of that. So in a sense, what you could wonder is, are we done? I mean, is it a nice discussion next to this question of where do the symbols come from? But in a sense, one may argue, well, we have already quite a lot of progress there and a lot of different frameworks, and of course we can improve them, but conceptually there is already a lot done. And actually we also saw that, and I just was happy that I could take now the screenshot, because I was just taking a screenshot of Yann yesterday, but now I could also take the screenshot of Bernhard referring to Yann. So all these different questions, and how do we get reasoning in there? How do we get causality in there? Seems to be very, very big. And yeah, there are some approaches. But I think we are not there yet. And this is very important. And I'm also happy that Klaus Robert Müller was giving a talk, although about a slightly different topic here. But I think we also understand that these systems we are building are getting quite complex. And maybe because of that, they become a kind of black box, right? We would like to better understand what is going on there, right? For a particular output here, for example, using relevance propagation, we would like to understand what is the important part of the input that led to maybe the decision or had most impact on the output, on the predictions. Now, to be honest, I think XAI, explainable AI, is amazing, but it's somehow maybe also not really what we need in the long run. I mean, it's the first step, but not the last step. So let me illustrate that here. So with these kinds of techniques, you can do interesting things. You can ask for explanations, right? So you get the scene, for example, and you could, if you know that the concept is something like there are a large cube and a large cylinder, you can now ask your system, explain me your decision, for being a positive example here, and you get an illustration, right? But most of the explainable AI techniques, they do not suggest how to fix this. If there's something wrong, it's a bit like I don't know whether you know Prolog, but Prolog, if something is really wrong, it typically gives back no as an answer, right? It's a bit frustrating. So you would like to also debug the system and maybe do not start from scratch. So you would like to somehow close the loop. And for example, you can close the loop by asking a user. There are different approaches for that. Maybe one of the earliest one was this work on right for the right reasons by Ross et al., where they assume a differentiable loss. We were extending that to a model agnostic one by making use of perturbations. So the user can give feedback or another system saying, yes, it is an example for the concept, but it's not because of those pixels, right? So you can make a big step and make use of this explanation to essentially implicitly change a bit of the loss function. At least that's one way of viewing it. And I think we had another interesting talk today by Martin Möller about this question of maybe we need more flexibility in the loss function. So that's maybe one way here. And we also applied that to really interesting data on understanding hyperspectral images in order to understand how plants are reacting to stress. And here's a particular biotic stress. So we inoculate particular diseases, and then we were trying to understand how they react to that using hyperspectral images. And the problem there was as well, if you use a convolutional neural network or some other, whatever your favorite one is, I mean, at least mainstream model, then it starts overfitting in the sense of making the right predictions, but really for the wrong reasons. And then by interacting with the experts, you can actually force us, in a sense, to select the at least more plausible, biologically more plausible reasons in the input modality. Now, problem is, even if you apply this explanatory interactive learning to the case that you see here, it fails somehow. And this is because these scenes that you see there are rather complex, right? And so it seems like a visual explanation is maybe not enough. So we thought, okay, cool. We saw that there are neural symbolic approaches like the one by Josh Tenenbaum and his group. So we applied these neural symbolic concept learners, and we thought, okay, now it's nice because maybe it talks about objects, and maybe it does not have clever Hans moments, but unfortunately, no, you just increase the capacity of the model, and so it's much easier even to fool it in a sense. I mean, it's a kind of self-fooling mechanism here. So what we then were doing is trying to understand whether we can also get a differentiable loss that is taking explanations into account. And we came up with a very simple kind of deep network that is also doing a bit of a reasoning, at least in terms of a concept learner, by first taking slot attention and then feeding that into the set transformer in order to reason also about this rather tabular representation. Now, you could, of course, use also a more advanced one. And for example, Hikaru was presenting a triple AI, a differentiable forward chaining inference algorithm that I think is also interesting for the database world, but that's a different story. I just want to highlight we were focusing on a simple setup here to really not add too much capacity again. Now, you can use, of course, this more complex model and differentiable model also to provide feedback both on the visual modality as well as on the tabular modality here. So essentially you have now two loss terms that are talking about your explanation, and essentially you're masking the stuff that the gradient should not consider. So essentially you're saying, don't use that part, don't use that part in the image, don't use that part in the table. But because you have a symbolic representation, you can actually give now feedback that is generalizing across different images. So you could really write down even something like, please never make use of a gray box to justify your decision. So it's interesting because we can talk about feedback implicit, we can provide implicit feedback that was not present in a sense in the example, and you can just provide general feedback. And then all of a sudden, because that also has impact, of course, on the visual part, on the slot attention module, you really get finally the explanations that you would like to have also in the visual modality. So what we are currently working on is pushing that forward, what is called the Bongart's problems. So these were problems developed originally to argue that neural networks were not really good for solving problems that humans can do in a sense. So this is back in the 70s. And we think we can now revisit by at least differentiable representation, which include both the vision module as well as a reasoning module. I'm not going into details here, but it seems to work, very initial results. It's quite interesting that you can just use both and they somehow support each other. So overall, I would argue there's still a lot to be done, and I hope you have seen it. So even if you make them more expressive, of course, clever Hans moments are there, but it's also nice because we can provide feedback now on the semantic level, and their symbols really help because we can communicate, and I would love to have a formal language there. But of course, you can imagine now also to replace by some transformer or some deep NLP model to also do the communication with the user. But I think we are not done for other reasons. So let's revisit what is happening here and imagine that I'm showing you the same image, but I'm asking you now, what is behind the red object if I rotate the scene by 90 degrees, whatever exactly it now means to rotate by 90 degrees. Or again, thank you to Bernhard, remember his example. And we start with his first image and we ask, is there a viewpoint so that I see a chair here? Right? So it seems like we have to understand, even when working with images with three-dimensional representations. And I think that's not really easy to do. So we got inspired by neural radiance functions. And we were wondering whether we can have an object-based neural radiance function approach here as well. So instead of going for the nerve directly, and also instead of now trying to put in extra knowledge in there by, for example, looking at a view encoder here or even a variational autoencoder here, we were trying to place again slot attention in there, and then per slot get a nerve. So essentially we are trying to estimate a set of nerves where each nerve is encoding one object. And if you manage that, then you get both an object-based three-dimensional representation, and of course you can rotate and take any perspective of the scene if you can do that. And so we managed, I'm not going into details, but it's interesting on the way you can also understand that some parts in the nerve are actually a probabilistic model. So in particular, if you walk along this ray trace and along the ray and try to understand whether something should be rendered or not, you can make a link to Poisson processes. And this is giving us the tool to actually talk about sets of these models. So we are talking now about a set of, for now, independent Poisson processes that are giving rays to whether you should get a color there or not in the ray tracing. And I think it's also very interesting to go over there into correlated Poisson processes. For example, making use of Poisson sum product networks. But let's see. But the game we are playing here for now is maybe, okay, we don't get a high visual fidelity, but we get a more usable representation for reasoning. And I think this is very much interesting because overall, we are still not there, right? I mean, all our models that we see so far, impressive progress, but common sense, we are not really there yet. And that's what we need in order to tackle something like the third wave of AI, right? Ultimately, I think we all want to have AI systems that can acquire human-like communication and reasoning capabilities with the ability to recognize new situations and adapt to them. And for that, at least object-based representation seems very interesting. Whether then the reasoning is implemented in neural fashion or not, I'm agnostic to that. I just want to solve these very challenging and interesting problems. Thanks.
Thank you, Christian, for this nice presentation, the last one in our workshop. Do we have questions? I would have one maybe to your very last slide. You're arguing that machines do not have common sense yet. How would you define common sense?
Yeah, that's why I like this idea yesterday that we talked about, right? It's not just world knowledge to put in there and then you can start reasoning. And to be honest, I don't think it's just reasoning. It's really this question of what is intuition in the end, and can we define mathematical term what is intuition? And maybe intuition is something like looks like reasoning, but we don't know, and it's the black box of Daniel Kremers, and I can't open it, but it's a wonderful answer you're giving to me. So I'm not claiming that reasoning is the answer to common sense, but I like the idea that we need actually something like a set of models that are maybe on the fly compiled to give you an answer. And this compilation should involve some formal reasoning or aspects at least of that. But to be honest, I'm also very much with Josh Tenenbaum, saying maybe we can't really get logical reasoning all the time right, because there are time constraints, right? And keeping it simple is maybe the trick in order to survive in a complex model world. Sorry. So, but I would argue our vision is that we need something like systems AI, a bit like systems biology, and we have to understand how to safely combine different AI models. So it's a bit like what Volker Markel was talking about, now combined with different deep learners, also planners, logical reasoning. And we are just wondering, can we provide the foundations for that so it's safe to combine them and you don't have to wonder about differentiability and whatever. But yeah, you see, I have no clue answer. It's just a vision.
Do we have other comments, feedback, maybe also questions? I don't know if Bernhard or Jean are still in the call, if we have questions to either of these. I would have a question. I don't know, Bernhard, are you still listening in? Because Bernhard has a commitment. No, maybe he's busy. But
Bernhard just put something into the chat. So
yeah, I know he has another commitment, so he may not be available. Let's close this session, and thanks everyone for attending, for joining. This is now the end of the public stream. Thank you so much for being with us. Thanks to all the speakers for their great presentations and the lively discussions. I think it was a great success in my view. I've really enjoyed this workshop. Thank you.
Yeah, thank you very much for to the organizers.
Yes, thanks for the organizers.
Is the organizers, but Daniel did all the work because I'm in New York and with the time difference, so he did all the work. So thank you. I think he did a great job. So
thank you, Jean.